Welcome back to another journey into the unknown. Tonight we're diving deep into one of the most fascinating paradoxes of human exploration. Picture this. You're sitting in your home right now, perhaps looking at the night sky through a window, marvelling at the stars above. Meanwhile, beneath the waves of Earth's oceans, there exists a world more alien, more mysterious, and less understood than the surface of Mars, a planet that sits, on average, 140 million miles away from where you're sitting right now. It sounds impossible, doesn't it? We've sent multiple spacecraft to Mars. We've landed rovers that have driven for miles across its rusty surface. We've mapped nearly every inch of the red planet from orbit with stunning clarity. And yet down here on Earth, in the crushing depths of our own oceans, vast regions remain completely unknown to us. Not just unexplored, but genuinely unknown in ways that might surprise you. The ocean covers approximately 70% of our planet's surface. That's about 139 million square miles of water, containing more than 99% of all the living space on Earth. Within those depths swim creatures we've never seen, landscapes we've never mapped, and mysteries we've only begun to comprehend. The deepest parts of the ocean, places like the Mariana Trench, plunge to depths of nearly 7 miles below the surface. To put that in perspective, if you placed Mount Everest at the bottom of the Mariana Trench, its peak would still be more than a mile underwater. Now here's where it gets truly mind-bending. As of June 2024, only 26.1% of the global seafloor has been mapped using modern high-resolution sonar technology. That means nearly 3/4 of the ocean floor remains unmapped at any meaningful detail. But it gets even more remarkable. When we talk about actual visual exploration, about human eyes or cameras actually seeing the seafloor, the numbers become almost incomprehensible. According to research published in 2025, humans have visually observed only 0.1% of the deep ocean floor. That's not 1%. That's 1/1000th of 1%. That's an area roughly equivalent to the size of Rhode Island. Meanwhile, we've mapped 100% of Mars's surface to a resolution of about 5 kilometers. Nearly 98% of the Martian surface has been mapped at resolutions finer than 100 meters. That's roughly the same resolution we've achieved for only about 10 to 15% of our ocean floor. And more than 60% of Mars has been mapped at resolutions around 20 meters, allowing us to see features the size of a house. Think about that for a moment. We know the contours, the craters, the canyons, and the mountains of a planet tens of millions of miles away better than we know the floor of the body of water that covers most of our own world. But why? How did this happen? How did we end up with better maps of a distant alien world than of the depths beneath our own feet? The answer, as you might expect, is complicated. It involves physics, economics, politics, engineering challenges, and even psychology. It tells us something profound about human nature, about what captures our collective imagination, and about the very different challenges posed by exploring inner space versus outer space. Tonight, we're going to unravel this paradox together. We'll journey through the history of both ocean and Mars exploration. We'll dive into the technical nightmares that make ocean exploration so difficult. We'll examine the strange life forms thriving in Earth's deepest places, creatures that might hold clues to life on other worlds. We'll look at the economics and politics that have shaped exploration priorities, and we'll consider what the future might hold for both frontiers. So settle in, get comfortable, and prepare for a journey that will take us from the crushing pressures of the deepest trenches to the airless plains of Mars and back again. Because understanding why we know more about Mars than our own oceans isn't just about exploration. It's about who we are as a species, what drives us forward, and what mysteries still await us in the darkness, whether that darkness is found above us or below. Before we go further, we need to address something fundamental. What do we actually mean when we say something has been explored? Because the comparison between ocean and Mars exploration isn't as straightforward as it might seem at first glance. Exploration exists on a spectrum, with different levels of knowledge and different types of observation. When we say Mars is better explored than Earth's oceans, we need to be precise about what that means, because the answer changes depending on which metric we use. Let's start with Mars, because in some ways it's the simpler case. When we talk about exploring Mars, we're generally referring to three main categories of observation. First, there's orbital mapping. This is where spacecraft circle the planet, using various instruments to create maps of the surface. Different instruments provide different types of information. Cameras give us visual data, allowing us to see craters, mountains, valleys, and other geological features. Spectrometers analyze the light reflecting off the surface, telling us about the chemical composition of rocks and soil. Radar can penetrate below the surface, revealing buried structures and ice deposits. This orbital observation is comprehensive. Multiple orbiters have spent years studying Mars from above, and the result is that we have nearly complete coverage of the entire planet. The level of detail varies, but here's what we've achieved. The entire surface of Mars, all 55.9 million square miles of it, has been mapped to a resolution of about 5 kilometers. That means features larger than about 3 miles across show up in these maps. But we've done much better than that for most of the planet. About 98% of Mars has been mapped at resolutions better than 100 meters, meaning we can spot features the size of a football field. And for more than 60% of the planet, we have maps at 20-meter resolution, where individual large boulders become visible. Some areas have been studied in even greater detail. The Mars Reconnaissance Orbiter's high-rise camera can resolve features as small as 30 centimeters across. These ultra-high-resolution images cover only a tiny fraction of the planet, but they've allowed us to study specific sites of interest in extraordinary detail. We've watched avalanches as they happen. We've tracked the formation of new impact craters. We've examined the layers and canyon walls like geologists examining a road cut on Earth. Beyond mapping, we have surface exploration. This is where rovers and landers come in. Since 1976, when the Viking landers touched down, we've successfully placed 9 robotic emissaries on the Martian surface. Some, like the Soviet Mars 3 lander, operated for mere seconds. Others, like the Opportunity rover, worked for more than 14 years, far exceeding their planned mission lifetimes. Currently, 2 rovers, Curiosity and Perseverance, are actively exploring the surface, drilling into rocks, analysing soil, searching for signs of ancient microbial life. These surface missions add a different dimension to our knowledge. Orbital observations can tell us what the surface looks like and give clues about composition. But rovers can touch the rocks, can drill into them, can analyse them with sophisticated instruments. They've discovered that Mars once had liquid water flowing on its surface. They've found organic molecules. They've measured radiation levels, tested the soil, monitored the weather. The area directly explored by all these rovers combined is tiny compared to the planet's total surface, probably less than 1%. But the knowledge gained from these up-close investigations informs our interpretation of the orbital data, allowing us to extrapolate what we see in one location to similar features elsewhere. So when we say Mars is well explored, we mean we have comprehensive mapping from orbit at various resolutions, detailed surface observations from select locations, and an integrated understanding that combines both types of data. We know where the largest volcanoes in the solar system are located. We know where ancient river deltas once existed. We can track seasonal changes in the polar ice caps. We have weather reports from several different locations. We understand in broad strokes the planet's geological history. Now, let's turn to Earth's oceans, where defining explored becomes more complicated. Like Mars, we can talk about mapping and direct observation, but the situation is very different. The ocean presents challenges that Mars doesn't, but it also offers some advantages. Let's start with the good news. The entire ocean floor has been mapped, at least in a basic sense. Satellites can measure the height of the ocean's surface with extraordinary precision, and these measurements reveal something surprising. The ocean's surface isn't flat. It has bumps and dips that mirror the topography below. Where there's an underwater mountain, the extra mass pulls water toward it, creating a small bulge in the surface. Where there's a trench, the reduced mass results in a slight depression. By measuring these subtle variations in sea surface height, satellites can create maps of the seafloor below. These satellite altimetry maps cover 100% of the ocean floor. They've revealed thousands of previously unknown seamounts, underwater mountains that rise from the deep. They've helped us understand the layout of mid-ocean ridges, the vast volcanic chains that snake through the world's ocean basins. They've shown us where the seafloor is spreading and where tectonic plates are colliding. In that sense, we have mapped the entire ocean floor, and these maps have genuinely advanced our understanding of ocean geology. But here's the limitation. Satellite altimetry has a resolution of about 1.5 kilometers, roughly 1 mile. Features need to be at least that large to show up. That's actually coarser resolution than what we have for 100% of Mars. A seamount that's half a mile wide, potentially hosting unique ecosystems, won't appear in these satellite maps. A canyon, a slope, a field of boulders. Unless they're large enough, they remain invisible in this data. For higher resolution, we need ships equipped with multi-beam sonar systems. These instruments send out arrays of sound waves that bounce off the seafloor and return to the ship. By analysing the timing and strength of these echoes, they can create detailed three-dimensional maps of the bottom. Modern multi-beam sonar can achieve resolutions of 100 meters or better, comparable to the moderate resolution maps we have of Mars. But here's the challenge. Unlike satellites that can observe Mars from orbit continuously, ships move slowly and can only map the relatively small swath of seafloor directly beneath them. It's like trying to map a continent by walking across it with a flashlight in a straight line, over and over again, until you've covered every bit of ground. It takes time, it takes resources, it takes hundreds of ships spending years at sea, systematically sailing back and forth to ensure complete coverage. As of June 2025, about 27.3% of the global seafloor has been mapped with this high-resolution sonar technology. That's progress. The number has been steadily increasing as international efforts like the Seabed 2030 project work toward the goal of mapping the entire ocean floor by 2030. But it means that 72.7% of the seafloor still hasn't been mapped at resolutions comparable to what we have for nearly all of Mars. And then we come to visual observation, to actually seeing the seafloor with cameras or human eyes. This is where the numbers become truly remarkable. Remember, we've visually observed only about 0.001% of the deep ocean floor. The deep ocean, defined as waters deeper than 200 meters, or about 656 feet, covers roughly 66% of Earth's surface. Within that vast realm, humans and human-made cameras have set eyes on an area roughly equivalent to Rhode Island, America's smallest state. Why so little? Because visual observation requires getting very close. Light doesn't penetrate far in seawater. Even in the clearest ocean water, sunlight becomes negligible below about 1,000 meters. In the deep ocean, it's pitch black. To see anything, you need to bring lights, which means bringing a vehicle, either a submersible with humans aboard, or a remotely operated vehicle, or an autonomous underwater vehicle. These vehicles are expensive to build and operate. There aren't many of them, and they can only observe a tiny area at a time, maybe a few meters around them, as they slowly traverse the seafloor. Since systematic deep-sea exploration began in 1958, researchers have compiled 43,681 records of deep-sea dives that included optical imaging. That sounds like a lot until you consider the vast area of deep-sea floor. Using two different methods to estimate coverage, one tracking the paths vehicles travelled, another using time spent on the bottom, researchers calculated that we visually observed between 822 and 1,476 square miles of deep-sea floor. Compare that to the roughly 120 million square miles of deep ocean floor, and you get that 0.01% figure. It's worth noting that this calculation only includes records that are publicly accessible. Oil and gas companies, telecommunications companies laying undersea cables, and military operations may have explored more of the seafloor, but if they haven't made those observations public, they don't contribute to scientific knowledge. So when we compare ocean and Mars exploration, we need to be specific. For basic mapping showing major features, both are completely covered, though Mars has better resolution overall. For high-resolution mapping showing details at the scale of individual buildings or boulders, we've mapped most of Mars but less than 30% of the ocean floor. For actual visual observation, with cameras and vehicles on location, we've explored far more of Mars than of Earth's deep ocean. Multiple rovers have travelled many miles across the Martian surface, seeing and analysing their surroundings. Meanwhile, the combined visual observations of all deep-sea expeditions in history have covered an area smaller than the smallest US state. The comparison reveals something important. Both places have been explored, but in different ways and to different depths. Mars has been comprehensively mapped from orbit and selectively examined up close. The ocean floor has been completely mapped at low resolution, partially mapped at high resolution, and barely seen up close at all. Both are mysterious, both hold secrets, but the type of mystery differs. On Mars, we know what's there broadly speaking, and we focus our up-close investigations on the most interesting features. In the ocean, large regions remain unmapped at useful resolutions, and vast areas have never been visually observed at all. This sets the stage for everything else we'll discuss, because to understand why this situation exists, we need to look at the history of how both frontiers were explored, the technical challenges each presents, and the human factors that shaped exploration priorities. Let's begin with the ocean, humanity's first frontier, where exploration stretches back thousands of years, but deep-sea investigation is barely older than the space age itself. The ocean has captivated human imagination since our ancestors first gazed upon its vastness. Ancient civilizations built ships and sailed beyond sight of land, relying on the stars, the sun, and hard-won knowledge to navigate waters that could be generous or deadly. The Phoenicians sailed throughout the Mediterranean and beyond. Polynesian navigators used wave patterns and bird behavior to find tiny islands across the vast Pacific. These were feats of remarkable skill and courage, but they were surface explorations. The depth below remained unknown, inaccessible, as alien as any distant planet. For most of human history, anything deeper than 100 feet or so was effectively unreachable. Free divers could descend to depths of perhaps 60 or 70 feet before the pressure became unbearable and the need for air overwhelming. The pressure increases by about 1 atmosphere, roughly 14.7 pounds per square inch, for every 33 feet of depth. At 100 feet down, the pressure is 4 times what it is at the surface. Your lungs compress. Your body absorbs nitrogen in ways that can be dangerous. Ancient and medieval divers understood these dangers through bitter experience, though they didn't understand the underlying physics. The first real tools for exploring beneath the surface came in the form of diving bells, chambers filled with air that could be lowered into the water. Aristotle wrote about diving bells being used as early as the 4th century BC. By the Renaissance, diving bells allowed workers to spend extended periods underwater for salvage operations or construction. But they were limited. They couldn't go deep. The air inside them compressed as depth increased, limiting how far they could descend. And they couldn't move around, they simply hung there, allowing divers to work in one location. The development of hardsuit diving gear in the 1800s improved things considerably. These were essentially wearable diving bells, suits of armour with air pumped down from the surface through a hose. A skilled diver in a hardsuit could work at depths up to several hundred feet, performing salvage operations, conducting underwater construction, exploring shipwrecks. But this was still surface exploration of the seafloor in shallow waters. The truly deep ocean remained beyond reach. The first scientific expedition to really study the deep ocean was the HMS Challenger expedition, which sailed from 1872 to 1876. This British naval vessel, modified for scientific research, travelled nearly 70,000 nautical miles, collecting samples, measuring ocean depth, studying water temperature and chemistry, and dredging up creatures from the deep. The expedition discovered thousands of new species and essentially founded the field of oceanography. They measured depths exceeding 5 miles in what we now call the Challenger Deep, the deepest known part of the ocean in the Mariana Trench. But the Challenger expedition, for all its achievements, could only observe from the surface. They could lower thermometers and sampling devices, could dredge the bottom and see what came up, but they couldn't go down themselves. They couldn't see the deep ocean. The creatures they collected were dead, often damaged by the rapid pressure change as they were brought to the surface. The environment of the deep ocean remained, in a very real sense, unknown. That began to change in the 1930s with the development of the bathysphere, a spherical steel chamber that could be lowered into the ocean depths on a cable. William Beebe and Otis Barton set records with their bathysphere dives off Bermuda, reaching depths of 3,028 feet in 1934. Peering through quartz windows, they saw bioluminescent fish, strange jellies, creatures never before seen alive. Beebe's accounts of these dives, published in National Geographic and in books, captured public imagination. But the bathysphere had severe limitations. It dangled helplessly on its cable. It couldn't move around. It relied entirely on the ship above for power and safety, and it couldn't go very deep by modern standards. The next major advance came with the bathyscaphe, a deep-diving submersible that could move independently. The Trieste, designed by Auguste Piccard and his son Jacques, made its historic dive to the bottom of the Challenger Deep on January 23, 1960. Jacques Piccard and US Navy Lieutenant Don Walsh spent about 20 minutes at a depth of 35,197 feet, nearly 7 miles down, the deepest point on Earth. They saw a flatfish and a shrimp, proving that life existed even in these most extreme conditions. It was a remarkable achievement, but in some ways it was also a dead end. The Trieste was expensive to operate, cumbersome, and could only reach the bottom and return. Meaningful exploration of the deep sea floor would require vehicles that could maneuver and work at depth. That capability arrived in the 1960s with the development of modern research submersibles like Alvin, built in 1964 and still in operation today after numerous upgrades. Alvin could carry scientists to depths of thousands of feet, later improved to over 20,000 feet, and more recently to over 21,000 feet after a major upgrade completed in 2022. Crucially, Alvin was maneuverable. It had thrusters, could move around, could approach features of interest, could collect samples with mechanical arms, could spend hours on the bottom systematically exploring. Alvin and submersibles like it transformed ocean exploration, but perhaps nothing demonstrated their value more dramatically than the discovery of hydrothermal vents in 1977. Scientists aboard Alvin were exploring the Galapagos Rift, a geologically active region where tectonic plates are spreading apart. They expected to find some hot water seepage, perhaps some interesting chemistry. What they found revolutionized our understanding of life on Earth. At these underwater vents, superheated water, reaching temperatures of 400 degrees Celsius or more, blast from the seafloor, carrying dissolved minerals that precipitate out and form towering chimneys, some reaching heights of several stories. These black smokers and white smokers, named for the colour of their mineral plumes, create an environment that seems incompatible with life. The water is scalding, toxic with hydrogen sulfide, crushed by immense pressure. No sunlight reaches these depths, and yet these vents teem with life. Giant tube worms, some reaching lengths of 8 feet, cluster around the vents. Mussels and clams carpet the rocks. Crabs, fish and octopuses prowl this alien landscape. The discovery completely upended existing theories about the requirements for life. Every ecosystem known to science, everyone believed, ultimately depended on the sun, Plants capture solar energy through photosynthesis, and everything else eats the plants or eats things that eat the plants. But at hydrothermal vents, there's no sunlight and no photosynthesis. Instead, bacteria use the chemical energy from the vent fluids, converting hydrogen sulfide and other compounds into organic matter through chemosynthesis. These bacteria form the base of a food chain completely independent of the sun. The implications extended far beyond marine biology. If life could thrive in the darkness of the deep ocean, utilizing chemical energy instead of sunlight, then maybe life could exist in other seemingly inhospitable places. Europa, Jupiter's ice-covered moon, likely has a liquid ocean beneath its frozen surface. Enceladus, a moon of Saturn, definitely does. Both worlds are far from the sun, but both have geological activity that could create environments similar to Earth's hydrothermal vents. The discovery of vent ecosystems made the search for extraterrestrial life suddenly seem more promising. Following the discovery of hydrothermal vents, deep-sea exploration accelerated, though it remained limited by the small number of vehicles capable of reaching great depths. The Japanese submersible Kaiko, an unmanned vehicle, explored depths approaching 7 miles in the late 1990s and early 2000s before being lost at sea. In 2003, the Nereus, built by Woods Hole Oceanographic Institution, could reach full ocean depth and operated successfully for several years before imploding, while exploring the Kermadec Trench in 2014. That implosion highlighted the extreme dangers of deep-sea exploration. The pressure at full ocean depth exceeds 16,000 pounds per square inch, more than 1,000 times the atmospheric pressure at sea level. Materials that seem strong at the surface can fail catastrophically under such conditions. In 2012, film director and explorer James Cameron made a solo dive to the Challenger Deep in his specially designed submersible, the Deep-Sea Challenger. Unlike the brief visit of Trieste 52 years earlier, Cameron spent several hours on the bottom, collecting samples, filming and exploring. The footage and samples brought back advanced our understanding of the deepest environment on Earth, but the expedition also highlighted how little we've explored these regions. Full ocean depth capability remains rare, with only a handful of vehicles in the world capable of reaching the deepest trenches. Most deep-sea exploration today relies on remotely operated vehicles, or ROVs, and autonomous underwater vehicles, or AUVs. ROVs are tethered to ships via cables that provide power and allow real-time control. Scientists on the ship can pilot the ROV, maneuver it to examine features of interest, use its manipulator arms to collect samples, all while watching live video feeds. AUVs, by contrast, operate independently, following pre-programmed missions without direct human control. They're particularly useful for mapping large areas or conducting surveys in places where a tether would be impractical, such as under ice sheets. These robotic explorers have dramatically increased the pace of ocean discovery. In 2024 alone, multiple expeditions made remarkable finds. Scientists exploring seamounts off the coast of Chile discovered more than 100 potentially new species, including deep-sea corals, glass sponges, squat lobsters, and amphipods. They mapped 50,777 square kilometres of previously uncharted seafloor and discovered 4 previously unknown seamounts, underwater mountains that rise thousands of metres from the surrounding seafloor. One of these seamounts stands 3,530 metres tall, more than twice the height of the Burj Khalifa, the world's tallest building. In October 2024, scientists announced they had discovered animals living in cavities deep beneath the seafloor itself, in the fractured rock under hydrothermal vents. Until this discovery, scientists thought only microbes could survive in such environments. Finding multicellular animals, including giant tube worms and various types of worms and snails, living in this subsurface habitat opened up yet another frontier for exploration. Another 2024 expedition discovered a ghostly white amphipod at a depth of nearly 8,000 metres in the Atacama Trench. Despite being only 4 centimetres long, this, tiny creature is an apex predator in its environment, using specialized raptorial appendages to capture prey. It was named Dulcibella camanchaca, with camanchaca meaning darkness in the languages of the Andean peoples, a fitting name for a creature living in one of Earth's most extreme environments. Perhaps one of the most surprising discoveries of 2024 was what researchers called dark oxygen production in complete darkness on the deep sea floor. Scientists found that metallic nodules on the seafloor, sitting in areas with no sunlight whatsoever, appear to be producing oxygen through some electrochemical process. This discovery could fundamentally change our understanding of how oxygen cycles work and raises new questions about the origins of life. These recent discoveries emphasize how much we still don't know about our own oceans. Each expedition reveals new species, new habitats, new phenomena. The Salas y Gomez Ridge and Nazca Ridge off Chile, where many recent discoveries have occurred, had fewer than 100 documented species before 2024. After just a few months of intensive exploration, that number jumped to over 300, an increase of more than 20%. And scientists estimate they may have discovered more than 100 entirely new species, though formal identification of new species takes years. Globally, scientists estimate there may be between 700,000 and 1 million species in the ocean, excluding microorganisms, which would add millions more. Of these, roughly 2/3 have yet to be discovered or officially described. About 2,000 new marine species are accepted by the scientific community each year, but at that rate, cataloguing even the species we think exist would take centuries, and that's assuming we find all of them before they go extinct. The history of ocean exploration, then, is one of steady progress punctuated by revolutionary discoveries, but it's also a history of limitations. We've only been able to explore the deep ocean for about 70 years, and for most of that time, we've had very few vehicles capable of reaching the greatest depths. Even today, with improved technology, only about 10 submersibles worldwide are certified for deep ocean travel. The ocean remains, in many ways, as inaccessible now as Mars was before the space age. But speaking of the space age, let's turn our attention skyward and trace the parallel history of Mars exploration. A history that in many ways has been more successful, more comprehensive, and certainly better funded than our exploration of the ocean depths. While humans were developing the means to explore the ocean depths, we were simultaneously reaching outward, developing technologies to explore space, and from the very beginning of the space age, Mars captured our imagination in ways that Venus, the Moon, and other worlds did not. Mars was close enough to be reachable, different enough to be interesting, and just similar enough to Earth to kindle dreams of what might be found there. The story of Mars exploration begins, as with most astronomical objects, with telescopes. Galileo first observed Mars through a telescope in 1610, but his instrument was too primitive to reveal much detail. As telescopes improved, astronomers began mapping the planet's surface features. In the late 1800s, Italian astronomer Giovanni Schiaparelli reported observing channels on Mars, which he called canali. In English, this was often translated as canals, implying artificial construction, and this mistranslation helped spark widespread speculation about Martian civilization. American astronomer Percival Lowell took this idea and ran with it, devoting years to observing Mars and producing detailed maps of the canal systems he believed he saw. Lowell convinced himself and much of the public that Mars was home to an advanced but desperate civilization, building vast canal networks to bring water from the polar ice caps to more temperate regions as their world dried up. This vision of Mars, dying but inhabited, permeated science fiction for decades. Of course, the canals didn't exist. They were optical illusions, the result of the human brain's tendency to connect random features into patterns, combined with the distortions created by Earth's atmosphere and the limitations of early telescopes. But the idea that Mars might harbour life persisted, and when the space age began, Mars was a prime target for exploration. The first spacecraft to successfully reach Mars was NASA's Mariner 4, which flew past the planet in July 1965. Its 22 images, transmitted back to Earth, shattered many romantic notions about Mars. They showed a cratered, barren landscape more reminiscent of the Moon than Earth. There were no canals, no cities, no obvious signs of life. Mariner 4 measured the Martian atmosphere and found it incredibly thin, with a surface pressure less than 1% of Earth's, composed mostly of carbon dioxide. This thin atmosphere meant liquid water couldn't exist on the surface. It would immediately boil away or freeze. Mariner 6 and 7, which flew past Mars in 1969, reinforced this bleak picture. Mars appeared dead, cold, and uninviting. But the Mariner 9 mission in 1971 changed everything once again. Unlike its predecessors, which made brief flybys, Mariner 9 entered orbit around Mars, becoming the first spacecraft to orbit another planet. When it arrived, a planet-wide dust storm obscured the surface. As the dust gradually settled over the following months, Mariner 9 revealed a Mars very different from what earlier missions had suggested. The spacecraft discovered massive volcanoes, including Olympus Mons, which at 13.6 miles high is the largest known volcano in the solar system, nearly 3 times taller than Mount Everest. It found Valles Marineris, a canyon system stretching nearly 2,500 miles across the planet and reaching depths of up to 4 miles, dwarfing Earth's Grand Canyon, and crucially, it found networks of channels that looked like dried-up river systems, suggesting that water once flowed on the Martian surface. Mariner 9 mapped about 85% of Mars's surface before contact was lost in October 1972, revolutionizing our understanding of the planet. The Soviet Union had been attempting Mars missions throughout this period, with mixed success. Mars 2 and Mars 3 arrived at the planet in 1971. Mars 2's lander crashed, but Mars 3 achieved the first soft landing on another planet, albeit briefly, transmitting data for only 20 seconds before falling silent. The orbiters from both missions functioned longer, returning 60 images and other data about the Martian atmosphere and surface. In 1975, NASA launched the Viking program, 2 identical spacecraft each consisting of an orbiter and a lander. Both reached Mars successfully in 1976, and both landers operated for years, far exceeding their design lifetimes. Viking 1 lasted until 1982, Viking 2 until 1980. The landers sent back the first colour images from the Martian surface, showing a rock-strewn landscape beneath a pink sky, coloured by dust suspended in the thin atmosphere. The Viking landers conducted biology experiments designed to detect signs of microbial life in the Martian soil. The results were puzzling, showing chemical reactions that could indicate biological activity, but could also be explained by unusual soil chemistry. Scientists remain divided about how to interpret Viking's biology experiments even today, nearly 50 years later. Most believe the results don't indicate life, but some researchers argue the data deserves a second look. The Viking orbiters continued the mapping work begun by Mariner 9, photographing the entire planet at much higher resolution. They revealed varied terrain including ancient cratered highlands, younger volcanic plains, polar ice caps that grew and shrank with the seasons, and those tantalizing dried-up riverbeds and outflow channels that suggested a wetter past. After Viking, Mars exploration hit a rough patch. A series of missions in the late 1980s and 1990s failed, both American and Soviet. Mars Observer, launched in 1992, lost contact just as it was about to enter orbit. Russia's Mars 96 mission failed to leave Earth orbit. Mars Climate Orbiter, launched in 1998, was destroyed when it entered Mars's atmosphere at the wrong altitude due to a unit conversion error in the navigation software, a costly and embarrassing failure. Mars Polar Lander, arriving in 1999, lost contact during descent and was never heard from again. These failures were frustrating, but the successes, when they came, were spectacular. Mars Global Surveyor, which entered orbit in 1997, operated until 2006 and completely transformed our understanding of Martian geology. Its laser altimeter created the first accurate topographic map of the entire planet. Its camera returned over 240,000 images at resolutions far better than Viking had achieved. And, crucially, it found evidence of recent water activity. Images showed gullies on crater walls that appeared to have formed recently, possibly from the melting of underground ice. Later observations even detected seasonal changes in some of these features, suggesting water might still flow on Mars under certain conditions. Mars Pathfinder, which landed in 1997, demonstrated a new landing technology using airbags to cushion the impact, a technique later used by other missions. It also deployed Sojourner, the first rover to operate on another planet. Sojourner was small, about the size of a microwave oven, and it didn't travel far, covering only about 100 meters during its 3 months of operation. But it proved the concept. A mobile rover could explore far more effectively than a stationary lander. This led to the Mars Exploration Rover mission, which landed 2 rovers, Spirit and Opportunity, at opposite sides of Mars in January 2004. Designed to operate for 90 days, both far exceeded their expected lifetimes. Spirit operated for over 6 years until it became stuck in soft soil in 2010. Opportunity operated for over 14 years, finally falling silent during a planet-wide dust storm in 2018. Together, they travelled dozens of miles across the Martian surface, analysing rocks, studying soil, and returning over 340,000 images. Both rovers found compelling evidence that liquid water once existed on Mars. Opportunity, exploring what appeared to be an ancient lake bed, found minerals that only form in the presence of water. Spirit found evidence of explosive volcanism and hot springs, environments that could potentially have harboured life. The rovers demonstrated that Mars was once warmer and wetter, with conditions that might have been suitable for life. Mars Reconnaissance Orbiter, arriving in 2006, carries the most powerful camera ever sent to another planet. Its high-rise camera can resolve features as small as 30 centimeters across from orbit, allowing it to capture stunningly detailed images of specific sites. It's been watching Mars for nearly 20 years now, observing seasonal changes, tracking weather patterns, capturing avalanches as they happen, imaging new impact craters as they form. It's also served as the primary communication relay for surface missions, transmitting more than 95% of all data from the Spirit and Opportunity rovers back to Earth. In 2012, the Curiosity rover landed in Gale Crater, a site chosen because it appeared to have been a lake billions of years ago. Curiosity is much larger than Spirit and Opportunity, about the size of a car, and it's nuclear-powered, allowing it to operate regardless of seasonal dust storms or the amount of sunlight reaching its location. Its sophisticated instruments can drill into rocks and analyse their composition in extraordinary detail. Curiosity has confirmed that ancient Mars had conditions suitable for microbial life. It's found organic molecules, detected methane in the atmosphere, though the source remains mysterious, and characterised the radiation environment that future human explorers would face. NASA's MAVEN orbiter, arriving in 2014, has been studying Mars's upper atmosphere and how the planet loses atmospheric gases to space. Its findings suggest that Mars once had a much thicker atmosphere, but over billions of years the solar wind has been stripping it away. This helps explain how Mars transformed from a warmer, wetter world to the cold desert we see today. The Mars InSight lander, operating from 2018 to 2022, studied the planet's interior by detecting Marsquakes and measuring heat flow from the deep interior. Its observations revealed that Mars's core is larger and less dense than previously thought, and confirmed that Mars remains geologically active, with numerous quakes detected during the mission. In 2021, NASA's Perseverance rover landed in Jezero Crater, another ancient lake bed. Perseverance is similar to Curiosity, but carries an upgraded suite of instruments specifically designed to search for signs of ancient microbial life. It's also collecting and caching samples of rocks and soil that a future mission hopes to bring back to Earth for detailed analysis. This Mars sample return mission, though troubled by cost overruns and schedule delays, remains a priority because analysing Martian samples in laboratories on Earth, with instruments far more sophisticated than anything that can be sent to Mars, could finally answer whether life ever existed on Mars. Perseverance also carried a small helicopter named Ingenuity, designed as a technology demonstration. Ingenuity was only supposed to fly 5 times, but it completed over 70 flights before damage to its rotor blades ended its mission in early 2024. It demonstrated that powered flight is possible in Mars's thin atmosphere, and that helicopters could serve as scouts for future rovers, surveying terrain ahead and identifying the best routes. Currently, 7 orbiters from 4 different space agencies are studying Mars from above: NASA's Mars Odyssey, Mars Reconnaissance Orbiter, and MAVEN, Europe's Mars Express and Trace Gas Orbiter, the United Arab Emirates Hope Orbiter, and China's Tianwen-1 Orbiter. Together, these spacecraft are continuously monitoring Mars, tracking weather, mapping mineral distributions, searching for subsurface water ice, and serving as communication relays for surface missions. On the surface, Perseverance continues its work in Jezero Crater, while Curiosity continues exploring in Gale Crater. China's Zhurong rover, which landed in 2021 as part of the Tianwen-1 mission, went into hibernation in 2022 and has not been heard from since, its fate uncertain. This fleet of spacecraft has made Mars the most extensively studied world in the solar system besides Earth. We have complete maps of the surface at various resolutions. We understand the planet's geological history in broad strokes. We know that water once flowed on the surface, that the climate was once dramatically different, that the conditions might have been suitable for life. We're monitoring current conditions, watching for changes, searching for any remaining habitable environments. Yet despite this comprehensive exploration, we still have fundamental questions about Mars. We don't know if life ever arose there. We're not certain whether liquid water still exists underground, though we've found strong evidence suggesting it does. We don't fully understand why the atmosphere was lost and whether it could be restored. We're still discovering surprises, like the discovery in 2018 of a possible liquid water lake beneath the South Polar ice cap, though that finding remains controversial. The history of Mars exploration has been one of steady progress with occasional setbacks. Roughly half of all missions to Mars have failed, a testament to the enormous technical challenges of interplanetary spaceflight. But the successes have been remarkable, giving us knowledge of another world that would have seemed impossible just decades ago. Now, having traced the parallel histories of ocean and Mars exploration, we can start to understand how we ended up knowing more about a distant planet than about the deep ocean on our own world. But history alone doesn't explain it. We need to understand the technical challenges because in many ways, exploring the deep ocean is fundamentally more difficult than exploring Mars. When people learn that we know more about Mars than about the deep ocean, a common reaction is disbelief. Mars is millions of miles away. The ocean is right here. How could it possibly be harder to explore? The answer lies in the fundamentally different challenges each environment presents. Space exploration is difficult but in predictable ways. Ocean exploration, particularly deep ocean exploration, presents a unique combination of problems that make it arguably the most technically challenging exploration we attempt. Let's start with the most obvious difference: pressure, or rather, the lack of it in space versus the abundance of it in the ocean. In space, the challenge is maintaining pressure. Spacecraft and spacesuits need to contain breathable air at a pressure humans can survive in, while the vacuum of space tries to pull that air out. It's certainly a challenge, but it's one we've solved quite effectively. The pressure difference between inside and outside a spacecraft is about 1 atmosphere, 14.7 pounds per square inch. The walls of the spacecraft need to be strong enough to contain that pressure and not leak, but the forces involved are relatively manageable. Now consider the deep ocean. Pressure increases by 1 atmosphere for every 33 feet of depth. At a depth of 1,000 feet, a fairly modest depth in oceanographic terms, the pressure is about 31 atmospheres, or 450 pounds per square inch. At the average depth of the ocean, about 12,100 feet, the pressure exceeds 365 atmospheres, or 5,300 pounds per square inch. At the bottom of the Mariana Trench, at a depth of about 36,000 feet, the pressure reaches approximately 100 atmospheres, or 16,000 pounds per square inch. That's equivalent to having 50 jumbo jets stacked on top of every square inch of surface area. This creates engineering challenges that are extraordinarily difficult to solve. Materials that are strong and rigid tend to be dense and heavy. To operate at depth, a submersible needs thick walls to resist the crushing pressure, but the thicker the walls, the heavier the vessel, and the more difficult it becomes to make it neutrally buoyant. You need flotation material that won't compress under pressure, but such materials are expensive and add volume to the vehicle. The sphere is the ideal shape for resisting external pressure because it distributes stress evenly across the surface. That's why virtually all deep-diving submersibles have spherical pressure hulls. But spheres are space inefficient, and connecting different modules together is mechanically complex. The pressure hull of Deep-Sea Challenger, the submersible James Cameron used to dive to the Challenger Deep, was so cramped that Cameron spent the entire dive in a nearly fetal position. Every penetration through the pressure hull, every port for cameras, every place where cables enter or exit, represents a potential failure point. Engineers must design seals that won't leak under enormous pressure differentials. They must test materials to ensure they won't fail catastrophically. The 2023 implosion of the Titan submersible during a dive to the Titanic wreck, killing all 5 people aboard, demonstrated the consequences of getting these designs wrong. At depth, there's no margin for error. If something fails, the pressure will crush the vehicle in milliseconds, faster than the human brain can register what's happening. The material science is extraordinarily demanding. Titanium is commonly used for deep submersible hulls because of its strength-to-weight ratio and resistance to corrosion, but it's expensive and difficult to work with. The Fenduji submersible, China's full ocean depth vehicle, required breakthroughs in titanium alloy development to create a pressure sphere strong enough to reach 36,000 feet, yet light enough to be practically useful. The sphere alone weighs 15 tons. Some components can be filled with incompressible fluids to equalize pressure, but this adds complexity. Batteries, electronics, instruments, all must be protected from the crushing pressure while still being able to function. The Deep-Sea Challenger used syntactic foam, a material made of millions of microscopic glass spheres embedded in resin, for flotation. Existing commercially available foams weren't adequate for full ocean depth, so lead engineer Ron Allum spent 18 months developing a new formulation that could withstand the pressure. Compare this to spacecraft design, where the challenge is exactly the opposite. The Mars rovers, for instance, need to be light because every kilogram of mass requires fuel to launch it from Earth, and later to slow it down for landing on Mars. Their bodies don't need to be particularly strong structurally. The pressure difference they face is just 1 atmosphere. The engineering challenges of Mars rovers relate more to power systems, thermal management, navigation, and autonomous operation than to basic structural integrity. Next, consider communication. In space, radio waves travel freely. Earth to Mars communication is straightforward, though the round-trip light time can be significant. At closest approach, about 3.1 minutes. At greatest distance, about 22 minutes. This time delay makes real-time remote control impossible, which is why Mars rovers must be highly autonomous. But the communication itself is reliable. Large dish antennas on Earth can pick up faint signals from spacecraft hundreds of millions of miles away. Underwater, radio waves are absorbed rapidly. For practical purposes, you can't use them for underwater communication beyond very short ranges. Instead, submersibles rely on acoustic communication using sound waves. Sound travels well in water, but acoustic communication has severe limitations. Bandwidth is extremely low. Sending a simple text message takes seconds. Transmitting high-quality images or video in real time is impossible. This is why many ROVs are connected to ships by cables, tethers that can provide high-bandwidth communication along with power. But tethers create their own problems. They limit how far the ROV can travel from the ship. They can snag on obstacles. In areas with strong currents or complex topography, managing a tether becomes a significant operational challenge. Autonomous underwater vehicles which don't have tethers must navigate and perform their missions completely independently, storing data that can only be retrieved when the vehicle returns to the surface. Positioning and navigation underwater is also far more difficult than in space. GPS signals don't penetrate seawater. Spacecraft can determine their position very accurately using star trackers, sun sensors, and communication with Earth. Mars rovers use similar techniques, supplemented by cameras that can identify landmarks. Underwater vehicles must rely on inertial navigation systems, which accumulate error over time, and acoustic positioning systems, which require transponders to be deployed on the seafloor in advance and have limited range and accuracy. Power is another significant challenge. Spacecraft can use solar panels, at least in the inner solar system where sunlight is sufficient. Mars rovers carry large solar arrays that provide ample power for their instruments and daily operations. Curiosity and Perseverance use radioisotope thermoelectric generators, devices that convert heat from radioactive decay into electricity, providing a steady power supply regardless of solar conditions. In the deep ocean, solar power isn't an option. No sunlight penetrates to depth. Batteries are the primary power source for submersibles, but batteries are heavy and have limited capacity. A deep-sea submersible might operate for 8 to 12 hours before needing to return to the surface to recharge. This severely limits how much exploration can be accomplished on each dive. The vehicles themselves face different operational challenges. Mars rovers need to navigate rocky terrain, avoid getting stuck in soft sand, and occasionally free themselves when they do get stuck. These challenges are real, and rover operators on Earth spend considerable time planning routes to minimize risks. But the rovers have time. They can sit still while operators analyze images and plan the next move. Dust storms are a hazard, particularly for solar-powered rovers, but they develop gradually. Submersibles and ROVs, by contrast, must contend with currents that can push them off course or slam them into obstacles. Visibility is often nearly zero, even with lights, due to particles suspended in the water. They must constantly adjust their buoyancy and trim to maintain position. Pilot workload is high, requiring constant attention and skill, and there's always the pressure, always the knowledge that they're operating in an environment that will destroy the vehicle instantly if something goes wrong. Temperature management poses different challenges in each environment. Spacecraft in sunlight can get very hot. In shadow, they get very cold. Mars surface temperatures range from about minus 125 degrees Celsius at the poles in winter to about 20 degrees Celsius at the equator in summer. Spacecraft and rovers need thermal control systems, but these are relatively straightforward. Radiators to dump excess heat, heaters to keep components warm, insulation to reduce heat loss. The deep ocean is cold, typically just above freezing regardless of latitude. But this is actually less of a challenge than the temperature swings faced in space. The bigger issue is heat transfer. Water conducts heat far more effectively than air or the vacuum of space. Electronics generate heat during operation, and that heat must be removed to prevent overheating, but it must also be contained enough to keep critical components above their minimum operating temperatures. Finding the right balance requires careful thermal design. Corrosion is a constant battle in the ocean environment. Seawater is highly corrosive, particularly to metals. Even titanium, though highly corrosion resistant, can suffer damage over long exposure. Aluminum corrodes rapidly in seawater unless specially protected. Brass, copper and other common engineering materials require protective coatings or are simply unsuitable for use. Galvanic corrosion, where two dissimilar metals in contact corrode more rapidly than they would separately, is a constant concern. Every material used on a submersible must be evaluated for its corrosion resistance and compatibility with other materials. In space, corrosion isn't a concern. The vacuum environment is actually quite benign from a corrosion standpoint. There's no oxygen to react with metals, no moisture to facilitate chemical reactions. Radiation is a concern, both for electronics and for materials that might degrade under prolonged exposure, but this is fundamentally different from the chemical attack of seawater. Field of view and sensory range also differ dramatically. On Mars, cameras can see to the horizon, which depending on the rover's elevation might be several kilometers away. This allows rover operators to identify interesting features from a distance and plan approaches. The thin atmosphere is generally clear, so visibility is excellent except during dust storms. In the ocean, visibility is measured in meters at best, often just a few meters even in relatively clear water. Particles suspended in the water scatter light. In deep water with high biological productivity, marine snow, the constant drift of organic material toward the seafloor, limits visibility to essentially zero beyond the immediate vicinity of lights. Sonar can see further, but sonar provides limited resolution and requires specialized interpretation. This limited visibility means that mapping the ocean floor is slow and painstaking. A ship with multi-beam sonar must sail over every bit of seafloor that needs to be mapped, a process that takes thousands of ship hours. An ROV, or submersible, exploring the seafloor can only observe a tiny area around itself at any given time. Contrast this with Mars orbiters, which can photograph vast swathes of the surface with each pass, building up global coverage relatively quickly. The practical result of all these challenges is that deep ocean exploration is staggeringly expensive per unit area explored. A single dive to the deep ocean floor costs hundreds of thousands of dollars when you factor in ship time, crew, equipment and support. Each dive explores only a tiny area, perhaps a few square kilometers if it's a mapping dive, much less if it's a detailed investigation of a specific site. Systematically exploring even a modest area of deep sea floor would require thousands of dives, costing billions of dollars. Mars exploration is also expensive, of course. The Perseverance rover mission cost about $2.7 billion, but that single mission has explored a wide area of Jezero crater, analysed dozens of rock samples, taken over 500,000 images, and will operate for years. The Mars Reconnaissance Orbiter, which cost about $720 million, has completely mapped the planet at moderate resolution and imaged thousands of sites at very high resolution. In terms of area explored per dollar spent, Mars exploration is vastly more efficient than deep ocean exploration. This efficiency difference helps explain why we've explored Mars so much more thoroughly than the ocean. It's not just about where we choose to spend our resources, it's about what those resources can actually accomplish. A dollar spent on Mars exploration produces more knowledge, more data, more explored area than a dollar spent on ocean exploration. That's not because space scientists are better at their jobs than oceanographers. It's because the physical environment of space is, paradoxically, easier to work in than the environment of the deep ocean. None of this is to say that Mars exploration is easy, or that ocean exploration is impossible. Clearly we've succeeded at both. But understanding the technical challenges helps explain the disparity in our knowledge. Mars is difficult to reach, but relatively straightforward to explore once you get there. The deep ocean is right here, but extraordinarily difficult to explore, with each meter gained requiring triumph over enormous pressure, limited visibility, corrosive water, and restricted communication. As our technology improves, As we develop better materials and more efficient vehicles, ocean exploration will become more feasible. Autonomous vehicles that can operate for months without human intervention, new communication systems, advances in battery technology, all of these will help. But the fundamental challenges won't go away. The pressure will still be crushing, the water will still be corrosive, the darkness will still be absolute. The deep ocean will always be one of the most difficult environments humans try to explore. And yet, for all these difficulties, the ocean remains worth exploring. Because despite being so much harder to reach than Mars, the ocean is home to an abundance and diversity of life that makes Mars, for all its mysteries, seem barren by comparison. Our extensive exploration of Mars has revealed a world of stark beauty and profound mystery. Through orbital observations, surface rovers, and comprehensive mapping, we've assembled a detailed picture of Mars as it exists today and as it was billions of years ago. But this knowledge has also raised new questions, showed us how much we still don't understand, and reframed the search for life elsewhere in the universe. Mars is a small world, about half the diameter of Earth, and with only about 11% of Earth's mass. Its lower gravity, about 38% of Earth's, means that geological features can grow much larger than they can on Earth before collapsing under their own weight. This is why Mars hosts Olympus Mons, a shield volcano that rises 16 miles above the surrounding plains, making it the tallest mountain in the solar system. The volcano covers an area roughly the size of Arizona. Its summit caldera, a collapsed crater at the top, is about 50 miles across and over a mile deep. Olympus Mons is so massive that if you stood on its summit, the slopes would extend beyond the horizon in all directions. You wouldn't be able to see the base of the mountain. The Tharsis region, where Olympus Mons and several other massive volcanoes are located, is itself a geological marvel. This volcanic plateau rises about 6 miles above the average Martian surface and spans approximately 2,500 miles across. The sheer mass of the Tharsis bulge has actually affected Mars's rotation, with the planet likely having reoriented itself so that Tharsis ended up near the equator, where the centrifugal force of rotation could best support the massive weight. On the opposite side of the planet from Tharsis lies the Hellas Impact Basin, a crater so large it's visible from Earth through telescopes. Hellas measures about 400 miles across and reaches depths of over 5 miles below the surrounding terrain. It's the third largest confirmed impact crater in the solar system and was formed by a collision so violent it likely affected the entire planet. Between these extremes lie vast plains, ancient cratered highlands, younger lava flows, mysterious regions of chaos terrain where the ground appears to have collapsed, and intricate networks of channels carved by flowing water billions of years ago. Valles Marineris, the Great Canyon system, stretches about 2,500 miles along the Martian equator, roughly the distance from New York to Los Angeles. It reaches widths of up to 430 miles in places and depths of over 4 miles, making Earth's Grand Canyon look like a scratch in comparison. The Martian surface we see today is ancient. Most of the terrain dates back billions of years, scarred by impacts from the heavy bombardment period early in the solar system's history. But Mars is not geologically dead. Marsquakes detected by the InSight lander prove the planet remains tectonically active, though far less so than Earth. Volcanic features show evidence of recent activity, recent by geological standards meaning within the past few million years. The planet's interior remains hot, and though the days of massive volcanic eruptions may be long past, Mars likely still experiences occasional volcanic activity. The Martian atmosphere, though present, is incredibly thin. Surface pressure averages about 0.6% of Earth's sea level pressure, too low for liquid water to exist on the surface under normal conditions. The atmosphere is 95% carbon dioxide with small amounts of nitrogen, argon, oxygen, and other gases. Despite being mostly carbon dioxide, the atmosphere is too thin to create a significant greenhouse effect, so Mars remains frigid, with average temperatures around -63 degrees Celsius. But the atmosphere, thin though it is, creates weather. Mars has clouds, fog and precipitation, though the precipitation is frozen carbon dioxide rather than water. Massive dust storms can envelop the entire planet, events that can last for months and have ended the missions of solar-powered rovers. The atmospheric pressure varies with the seasons as carbon dioxide freezes out of the atmosphere at the winter pole, then sublimes back into the atmosphere during spring. The polar ice caps are perhaps Mars's most dynamic features. Each pole has a permanent cap of water ice several miles thick, overlain by a seasonal cap of frozen carbon dioxide that grows in winter and sublimes in summer. The southern polar cap sits atop a region of unusual layered terrain, and in 2018 radar observations suggested there might be liquid water trapped beneath the ice, though this remains controversial and unconfirmed. Water, or more precisely the lack of liquid water and the evidence of past water, is central to our understanding of Mars. Today's cold, dry Mars bears little resemblance to the world that existed 3 to 4 billion years ago. That ancient Mars had a thicker atmosphere, warmer temperatures, and liquid water flowing on its surface. The evidence is overwhelming. Valley networks in the ancient highlands show dendritic patterns characteristic of rivers on Earth, formed by water flowing across the landscape. Outflow channels, some of the largest channels in the solar system, appear to have been carved by catastrophic floods, releasing volumes of water that dwarf anything in Earth's geological record. Crater lake deposits, sedimentary rocks, and minerals that only form in water all tell the same story. Ancient Mars was wet. Lakes and possibly even an ocean existed for extended periods. Perseverance, exploring Jezero crater, has found sedimentary rocks that could only have formed at the bottom of a lake. The rover has identified minerals, including clays and sulfates, that form through interaction with water. What happened to all that water? Some remains locked in polar ice caps and subsurface ice deposits. Mars Reconnaissance Orbiter has mapped extensive ice deposits buried beneath the surface at mid-latitudes, ice that could supply future human missions. But most of the water was lost to space. MAVEN's observations show that the solar wind, streams of charged particles from the sun, strips away the Martian atmosphere at a rate of about 100 tons per day. Over billions of years, this process removed most of the original atmosphere, and with it much of the planet's water. The water molecules broke apart in the upper atmosphere. The hydrogen, being light, escaped to space, and the oxygen either escaped or reacted with surface rocks. The loss of the atmosphere is tied to another key feature of Mars, its lack of a global magnetic field. Earth's magnetic field, generated by our planet's liquid iron core, deflects the solar wind, protecting the atmosphere. Mars once had a strong magnetic field, evidenced by magnetic minerals in ancient rocks, but it faded away billions of years ago as the core cooled and solidified. Without this protection, the atmosphere was vulnerable to erosion by the solar wind. This brings us to perhaps the most important question about Mars. Did life ever exist there? We don't know. We found no definitive evidence of past or present life. But we've established that ancient Mars had the key requirements: liquid water, energy sources, and organic compounds. The Viking landers in the 1970s conducted experiments to detect microbial life, with ambiguous results that most scientists interpret as chemical rather than biological. The Curiosity and Perseverance rovers have found organic molecules, but organic doesn't necessarily mean biological. Organic compounds can form through non-biological processes. The methane detected in Mars's atmosphere is particularly intriguing. Methane breaks down in the Martian environment within a few hundred years, so its presence means it's being replenished somehow. On Earth, most atmospheric methane is produced by biological processes, but it can also be generated by geological processes. The methane on Mars could be a sign of active biology, but it could just as easily come from chemical reactions in underground rock. The search for life on Mars has become more nuanced. Instead of looking for microbes crawling around on the surface, which seems unlikely given the harsh conditions, scientists look for biosignatures, chemical or physical markers that might indicate past life. Ancient rocks that formed when Mars was warmer and wetter might contain fossilized microorganisms or chemical signatures of past biological activity. Perseverance is collecting samples of Martian rock and soil, carefully selected from sites that might preserve biosignatures if they exist. These samples are being left on Mars's surface in a sample cache, ready for a future mission to collect and bring back to Earth. When those samples arrive in laboratories here, likely sometime in the 2030s if current plans proceed, scientists will be able to analyze them with instruments far too large and complex to send to Mars. That analysis might finally answer whether Mars ever hosted life. Meanwhile, the search continues on the planet itself. Perseverance is exploring terrain that shows clear evidence of ancient water, analysing rocks, searching for patterns that might indicate biological processes. Future missions might drill deep into the subsurface, where ice might protect any surviving organisms from the harsh surface environment. The polar regions, where ice exists near the surface, are another target for future exploration. We know a great deal about Mars, but each answer raises new questions. We understand that water once flowed on the surface, but we don't fully know where all that water went or whether significant amounts remain accessible. We know the atmosphere was lost, but we don't understand all the details of when and how this happened. We know the planet has a fascinating geological history, but many specifics remain unclear. And the question of life, perhaps the most important question of all, remains unanswered. But the knowledge we've gained is remarkable. From Earth, Mars appears as a reddish point of light in the night sky. Through our spacecraft, we've turned that point of light into a complete world with mountains and canyons, weather and seasons, a dramatic geological past and a potentially habitable history. We know Mars better than humans knew Earth just a few centuries ago. Now let's turn our attention back to our own planet, to the vast underwater realm that remains far more mysterious than the Red Planet, despite being just below the surface of our familiar oceans. If you were to drain Earth's oceans, the revealed landscape would be more dramatic and varied than Mars. Vast plains stretching for thousands of miles, interrupted by mountain ranges that make the Rockies and Himalayas look small, canyons deeper than anything on land, thousands of underwater volcanoes, many still active, mud volcanoes, underwater rivers, immense waterfalls where currents plunge over underwater cliffs. The ocean floor is not the flat, featureless plain early explorers imagined. It's a dynamic, complex environment that rivals any terrestrial landscape for geological drama. And yet, as we've established, nearly 3/4 of this landscape remains unmapped at any useful resolution. What we know comes from a combination of satellite altimetry, which provides low-resolution maps of the entire ocean floor, and ship-based sonar surveys, which have covered only about 27% of the seafloor at high resolution. The remaining area, roughly 100 million square miles, is effectively terra incognita, unknown territory on our own planet. The mid-ocean ridge system is Earth's longest mountain range, stretching more than 40,000 miles through the Atlantic, Indian, Pacific and Southern Oceans. This is where new oceanic crust forms as tectonic plates spread apart, where volcanic activity creates new seafloor, where hydrothermal vents pump mineral-rich fluids into the ocean. We've explored only tiny fractions of this vast system. Each expedition finds new vent sites, new biological communities, new geological features we didn't know existed. Seamounts, underwater mountains that don't reach the surface, number in the tens of thousands, possibly hundreds of thousands globally. Satellite altimetry has identified the largest ones, those tall enough and massive enough to create detectable bumps in the ocean surface. But smaller seamounts, anything under a mile or so tall, are essentially invisible to satellites. Ship-based surveys keep discovering them. In 2024 alone, several new seamounts were discovered and mapped off Chile's coast, including one nearly 2 miles tall that was previously completely unknown. These seamounts are biological hotspots. Currents flowing over and around them create upwelling that brings nutrients from the deep to the surface waters, supporting enhanced biological productivity. The seamounts themselves provide hard substrate in areas where the surrounding seafloor might be soft sediment, allowing different communities of organisms to thrive. Many seamounts host extensive cold-water coral gardens, with corals that can live for hundreds or even thousands of years. The recent discoveries off Chile exemplify what we're finding as we explore more intensively. In just a few months of expeditions in 2024, scientists documented more than 150 potentially new species on seamounts along the Nazca and Salas Güemes ridges. They found deep-sea corals in formations unlike anything seen before, glass sponges that can live for thousands of years, squat lobsters, sea urchins, amphipods, all potentially new to science. They photographed rare species like the Casper octopus, nicknamed for its pale, ghostly appearance, and captured the first footage of the Promcoteuthis squid alive in its natural habitat, a species previously known only from dead specimens pulled up in nets. The number of recorded species in that region jumped from about 1,000 before 2024 to over 1,300 after just a few months of focused exploration, an increase of more than 30%. And scientists estimate they've encountered many more new species that haven't yet been formally identified and described, a process that can take years. These discoveries aren't flukes or lucky finds. Every time scientists explore a new area of the deep ocean, they find new species, sometimes dozens of new species from a single expedition. This tells us something profound. We've barely scratched the surface of ocean biodiversity. Scientists estimate that somewhere between 700,000 and 1 million species inhabit the ocean, not including microorganisms. Of these, only about 1/3 have been discovered and described. That means there are potentially 500,000 or more species still unknown to science swimming in the ocean right now, creatures we've never seen, ecosystems we've never documented. The deep sea, below 200 meters, is Earth's largest habitat by volume, yet it's the least explored. It's also home to some of the strangest creatures ever discovered. Giant squid, reaching lengths of over 40 feet, remained legendary until photographs of living specimens were finally captured in 2004. Goblin sharks, with protruding jaws that can extend forward to capture prey, look like something from a science fiction movie. Vampire squid, despite their fearsome name, are actually gentle creatures that feed on marine snow, using light-producing organs to confuse predators. Barrel-eye fish have transparent heads and tubular eyes that can rotate to look up or forward. In the Atacama Trench, at depths approaching 8,000 meters, scientists recently discovered Dulcibella camanchaca, an amphipod that's an apex predator despite being only about 4 centimeters long. It has specialized raptorial appendages, folding arms with sharp edges, that it uses to capture smaller prey. This species lives in the Hadal zone, the deepest 45% of the ocean, an environment subjected to crushing pressure, near freezing temperatures, and complete darkness. The fact that a predator this specialized exists there suggests a complex ecosystem we've barely begun to investigate. But perhaps the most important discoveries in recent ocean exploration have been entire new types of ecosystems, environments that change our understanding of how life works. The discovery of hydrothermal vents in 1977 was just the beginning. Since then, scientists have found cold seeps, areas where hydrocarbons like methane seep from the seafloor, supporting communities based on chemosynthesis. They've discovered extensive beds of cold water corals in places previously thought to be nearly lifeless. They've found brine pools, underwater lakes of water so salty it doesn't mix with the surrounding ocean, creating underwater shorelines complete with waves. In 2024, scientists announced they had found animals living in cavities beneath the seafloor itself, in the fractured rock under hydrothermal vents. Until this discovery, Everyone assumed that only microbes could survive in this subsurface habitat. Finding giant tube worms, snails, and other animals living there opened up an entirely new frontier for exploration. If animals can thrive in these environments, how many other cryptic habitats exist that we haven't yet discovered? The 2024 discovery of dark oxygen production on the deep sea floor was another paradigm shifter. Scientists found that polymetallic nodules, potato-sized rocks containing manganese, iron, cobalt, and other metals, appear to be producing oxygen through electrochemical reactions in complete darkness. For our entire history of studying life, we've understood that oxygen in Earth's atmosphere comes from photosynthesis. Plants and phytoplankton use energy from sunlight to split water molecules, releasing oxygen as a byproduct. But here was oxygen being produced without any light at all, through a purely chemical process. The implications are profound. This discovery suggests oxygen might be produced in completely dark environments elsewhere, on moons or planets with subsurface oceans where photosynthesis is impossible. It could change our understanding of how oxygenic photosynthesis evolved on Earth, and it raises difficult questions about deep-sea mining, because the polymetallic nodules that produce this oxygen are the same ones that mining companies want to harvest for their metal content. The ocean floor itself is far more geologically active than most people realise. The mid-ocean ridges are sites of constant volcanism, with new crust forming continuously. Underwater eruptions are probably happening right now somewhere in the world's oceans, though most go unobserved and unrecorded. Submarine volcanoes can erupt with explosive force, the volcanic material sometimes reaching the surface and creating new islands. Underwater landslides, triggered by earthquakes or simply by accumulated sediment becoming unstable, can be enormous. Some ancient underwater landslides have moved hundreds of cubic miles of material, creating tsunamis that devastated coastlines. Recent mapping has revealed massive coral reefs in the deep sea, far larger than previously known. In January 2024, scientists announced they had mapped the largest deep-sea coral reef habitat ever discovered, covering an area larger than the state of Vermont off the southeastern coast of the United States. These cold-water coral mounds, created by corals that don't require sunlight, stretch for hundreds of miles at depths where no one expected to find such extensive reef systems. Current knowledge suggests that many geological features of the ocean floor remain undiscovered. Where the seafloor hasn't been mapped at high resolution, entire seamounts, canyons, or unusual formations might exist unknown to science. Even in mapped areas, high-resolution sonar reveals details that lower-resolution surveys miss. Scientists mapping seamounts off Chile in 2024 discovered that many had been significantly misidentified or mislocated in existing charts. Their precise positions, heights, and shapes were all different from what previous lower-resolution mapping had suggested. The chemical and mineral resources of the ocean floor are substantial but incompletely understood. Polymetallic nodules litter parts of the deep sea floor, representing vast deposits of manganese, nickel, copper, and cobalt. Massive sulfide deposits at hydrothermal vents contain high concentrations of copper, zinc, gold, and silver. Rare earth elements crucial for modern electronics exist in deep sea sediments. But we don't know the full extent of these resources, don't understand their exact distribution, and don't know what ecological damage their extraction might cause. Archaeological treasures rest on the ocean floor as well. Ships have been sinking for thousands of years, and the deep ocean is a remarkably good preserver of shipwrecks. Wood and metal that would decay rapidly on land or in shallow water can survive for centuries in the deep ocean's cold, low-oxygen environment. Each shipwreck is a time capsule, preserving artifacts and information about past cultures, trade networks, and historical events. But we don't know where most wrecks are located. Only a tiny fraction of the estimated 3 million shipwrecks on the ocean floor have been found and documented. The ocean floor is constantly changing. Currents erode sediment and transport it, sometimes for hundreds or thousands of miles. Underwater dunes migrate across the seafloor. Biological activity bioturbates the sediment, mixing and reworking it. Organisms create structures, from coral reefs to burrows to bacterial mats, that alter the local environment. Understanding these processes is important for understanding Earth's geology, chemistry and biology, but our understanding is based on observations from only a tiny fraction of the ocean floor. Climate change is affecting the ocean floor in ways we're only beginning to understand. Warmer water can hold less dissolved oxygen, and oxygen levels in the deep ocean are declining in many regions. This affects everything that lives there. Ocean acidification, caused by the ocean absorbing carbon dioxide from the atmosphere, affects shell-forming organisms, including many that live on the deep sea floor. Changes in ocean currents, driven by changes in water temperature and salinity, can alter the delivery of nutrients to deep-sea ecosystems. But we don't have comprehensive baselines for most of the ocean floor, so detecting and understanding these changes is difficult. The ocean floor represents the last great frontier on Earth, a vast unknown territory that's more extensive than all the continents combined. In many ways, it's more alien than Mars. Mars is a dead world with no life as far as we know. The ocean floor teems with life in an incredible diversity of forms, living in conditions we still barely understand. Mars's surface has been mapped to high resolution. Most of the ocean floor remains unmapped. We've sent multiple rovers to explore Mars. We've barely scratched the surface of ocean floor exploration. The disparity is striking, but it's not inevitable. It's the result of choices we've made, resources we've allocated, and priorities we've set. To understand why we've explored Mars more thoroughly than our own ocean floor, we need to look beyond the technical challenges and examine the economics, politics, and cultural factors that have shaped exploration priorities. At its core, the disparity between Mars and ocean exploration comes down to resources. Money? Yes, but also public attention, political support, and institutional infrastructure. These factors are interconnected, and together they've created a situation where we've invested far more in exploring Mars than in exploring the deep ocean, despite the ocean being right here and the red planet being millions of miles away. Let's start with the money, because nothing happens in exploration without funding, and the funding differences are stark. NASA's budget for fiscal year 2024 was approximately $24.9 billion. Not all of that goes to Mars or even to planetary exploration, of course. NASA funds Earth science, astrophysics, aeronautics research, the International Space Station, and many other programs. But substantial portions of NASA's budget support Mars exploration specifically. The Mars exploration program has received several $1 billion annually in recent years. The Perseverance rover mission, which landed in 2021, cost about $2.7 billion. The Mars Sample Return Program, though troubled by cost overruns, has been allocated roughly $950 million per year, with total costs expected to exceed $5 billion. Multiple Mars orbiters continue operating, each with ongoing operational costs. When you add it all up, the United States alone probably spends upwards of $3 to $4 billion per year on Mars exploration and related technology development. Other countries and space agencies also invest in Mars exploration. The European Space Agency's Mars Express Orbiter and Trace Gas Orbiter, China's Tianwen-1 mission, the United Arab Emirates Hope Orbiter, all represent significant investments. Globally, Mars exploration likely receives $5 billion or more per year in direct funding, with additional amounts spent on technology development and ground-based support. Now let's consider ocean exploration funding. NOAA, the National Oceanic and Atmospheric Administration, is the primary federal agency responsible for ocean exploration in the United States. NOAA's Office of Ocean Exploration and Research receives approximately $60 million per year. That's not a typo. The entire annual budget for NOAA's ocean exploration program is roughly equivalent to what it costs to operate a single Mars rover for 1 year. To be fair, That $60 million isn't the only funding for ocean exploration. Other parts of NOAA's budget support related activities. The National Science Foundation funds oceanographic research. The US Navy conducts extensive ocean mapping and research, though much of it is classified. Private organisations, universities and international partners all contribute. But even being generous with estimates, total US funding for deep ocean exploration probably doesn't exceed $500 million per year, and global funding for ocean exploration is likely under $2 billion annually. That means space exploration spending, particularly for Mars, outpaces ocean exploration spending by a factor of at least 3 to 1, possibly 5 to 1 or more. Some analyses have suggested the ratio is even more extreme. A 2013 report noted that federal space exploration spending exceeded ocean exploration spending by more than 150 to 1, though this may have overstated the case by not including all ocean-related spending. Regardless of the exact ratio, the trend is clear. We spend far more exploring Mars than exploring our own oceans. Why? Several factors contribute to this disparity, and they reinforce each other in ways that make changing the situation difficult. First, there's the matter of public interest and cultural significance. Space exploration, particularly human spaceflight, captures public imagination in ways that ocean exploration generally doesn't. When Neil Armstrong stepped onto the moon in 1969, an estimated 650 million people watched, about 20% of Earth's population at the time. That's a shared cultural moment few things can match. The landings of Mars rovers generate substantial public attention. The James Webb Space Telescope's first images were celebrated worldwide. Space missions make headlines. Ocean exploration can generate excitement, but it typically doesn't rise to the same level. James Cameron's 2012 solo dive to the Challenger Deep received significant media coverage, but nothing like the attention given to space missions. The discovery of hydrothermal vents in 1977 revolutionized biology, but most people have never heard of it. Recent discoveries of new deep-sea species make the news briefly, and then fade from public consciousness. This difference in public interest affects political support, which in turn affects funding. Elected officials respond to what their constituents care about. When space exploration is popular, supporting NASA is good politics. Presidents and members of Congress can point to space achievements as evidence of American leadership and technical prowess. The space program has symbolic importance that transcends its practical benefits. Ocean exploration lacks this same symbolic power. It's important scientifically, certainly. It's relevant to fisheries management, climate science, resource extraction, and other practical concerns. But it doesn't inspire the same dreams. We're going to Mars is a rallying cry that excites people. We're going to map the Nazca Ridge doesn't have quite the same ring to it, however scientifically important that work might be. The cultural difference extends to science fiction and popular media. As noted earlier, space dominates science fiction. Star Trek, Star Wars, Battlestar Galactica, The Expanse. These cultural touchstones are all set in space. They shape how people think about exploration and humanity's future. Ocean-based science fiction exists, but it's far less common. The Abyss, 20,000 Leagues Under the Sea, these are classics, but they're exceptions. For every submarine movie, there are probably 10 space movies. This cultural imbalance reinforces itself. Children grow up watching astronauts and space exploration, and some of them decide they want to become astronauts or aerospace engineers or planetary scientists. Universities develop strong programs in these fields to meet demand. Companies build spacecraft and instruments. An entire industrial and educational ecosystem develops around space exploration. Ocean exploration has its own ecosystem, certainly, with specialized programs and companies, but it's smaller and less prominent. There are strategic and military considerations as well. Space has always had military importance, from the earliest days when rockets were military weapons before they were launch vehicles. Satellites provide reconnaissance, communication, navigation, weather monitoring. all crucial for modern military operations. The connection between civil space programs and military applications has helped sustain political support and funding. NASA's budget is separate from the defense budget, but the technologies and capabilities NASA develops often have military applications, and this dual-use nature strengthens support. Ocean exploration has strategic importance too. Submarine warfare, mine detection, underwater surveillance, these are important military missions. The US Navy does extensive ocean mapping and research. But this work is often classified, contributing to military capabilities, but not to public knowledge or civilian science. The separation between military and civilian ocean exploration is sharper than it is in space, reducing the overall political coalition supporting ocean exploration funding. Economic interests play a role as well. The aerospace industry is huge, employing hundreds of thousands of people across many states. Companies like Boeing, Lockheed Martin, Northrop Grumman, SpaceX, and many others build spacecraft, rockets, and instruments. These companies and their employees have a direct interest in continued space exploration funding, and they lobby for it. Many congressional districts have aerospace jobs, giving local representatives a constituency reason to support NASA funding. Ocean exploration has economic constituencies too, including shipbuilders, instrument manufacturers, research institutions and fishing industries that benefit from better ocean knowledge. But these constituencies are generally smaller and less politically organised than the aerospace lobby. The companies involved are often smaller. The economic footprint is more diffuse. The political leverage is weaker. The way research funding is structured also matters. NASA is a civilian agency with a clear mission: space exploration and aeronautics research. Its budget, while subject to congressional approval and political pressures, is explicitly designated for exploration and science. This creates institutional momentum. NASA has infrastructure, expertise, and relationships with contractors and universities that enable large, ambitious missions. Ocean exploration funding is more fragmented. NOAA is the lead federal agency, but it has many other responsibilities besides exploration, including weather forecasting, fisheries management, and coastal zone management. Ocean exploration is just one of many NOAA missions, and it often competes for funding with more immediate operational needs. The National Science Foundation funds ocean research through grants to universities, but this is distributed across many individual projects rather than concentrated in large flagship missions. The Navy does ocean research and mapping, but this serves military objectives and isn't generally publicly accessible. This fragmentation makes it harder to build political support for increased ocean exploration funding. There's no single agency whose primary mission is ocean exploration, no clear champion within the federal government structure, no natural focal point for advocacy. Different agencies pursue different aspects of ocean research with different priorities, and coordination, while it exists, is incomplete. International cooperation plays out differently in space and ocean exploration. Space agencies have developed strong collaborative relationships. NASA works with the European Space Agency, the Japanese Aerospace Exploration Agency, the Canadian Space Agency, and others on various missions. The International Space Station exemplifies this cooperation. These partnerships spread costs, share expertise, and create diplomatic benefits that help sustain political support. Ocean exploration sees international cooperation too, with collaborative expeditions and data sharing. The Seabed 2030 project, which aims to completely map the ocean floor by 2030, is an international effort coordinating mapping activities from many countries. But ocean exploration partnerships often focus on specific regions or particular projects, rather than the kind of large, visible, multinational missions common in space exploration. The return on investment also differs in perception, if not in reality. Mars exploration promises answers to profound questions. Was Mars once habitable? Did life ever exist there? Could humans one day live on Mars? These questions capture imagination, and the potential answers seem momentous. the idea of discovering evidence of life on Mars, even ancient microbial life, would be one of the most significant scientific discoveries in history. Ocean exploration asks different questions. What species live in the deep sea? What geological processes shape the ocean floor? How do deep-sea ecosystems function? These are important questions with real scientific value and practical implications, but they don't have the same philosophical weight as, are we alone in the universe? Even though ocean exploration has answered profound questions, like the discovery that life doesn't need the sun, that chemosynthesis can sustain complex ecosystems, these discoveries don't quite match the cultural resonance of potential discoveries on Mars. The practical benefits of ocean exploration can actually work against it in terms of public funding. Because ocean research has clear connections to fisheries, shipping, resource extraction, and other commercial activities, there's an argument that private industry should help fund it. Companies that benefit from ocean knowledge, the argument goes, should contribute to generating that knowledge, and some do, particularly in areas directly related to their operations like oil and gas exploration. But much of the ocean isn't commercially valuable enough to attract private investment in exploration, and the public goods aspects of ocean knowledge, data that benefits everyone, insights into climate and ecosystems, scientific discoveries, require public funding to pursue. Space exploration faces similar arguments about private versus public funding. Companies like SpaceX, Blue Origin, and others are now major players in space. But the exploration of scientifically interesting places like Mars remains largely publicly funded because the timelines are too long and the payoffs too uncertain for private investment. The difference is that space has maintained strong public funding even as private space activities have grown, while ocean exploration funding has remained stagnant or even declined in real terms. All of these factors, economic, political, cultural, combine to create a situation where Mars exploration receives more funding, attracts more talent, builds more institutional capacity, and achieves more results, which in turn generates more public interest, which helps sustain funding. It's a positive feedback loop. Meanwhile, ocean exploration operates in a more constrained environment with less funding, less public attention, and less political support, which limits what can be achieved, which makes it harder to generate excitement and justify increased investment. It's not quite a negative feedback loop, but it's certainly not a virtuous cycle. Breaking this pattern would require a sustained effort to raise public awareness about ocean exploration, build political coalitions to support increased funding, develop institutional structures that give ocean exploration clearer priority, and demonstrate compelling results that capture public imagination. Some of this is happening. The success of programs like Schmidt Ocean Institute's expeditions, which have discovered hundreds of new species in recent years, shows what's possible with adequate resources. The Seabed 2030 initiative is making real progress toward the ambitious goal of completely mapping the ocean floor within this decade. But changing funding priorities is always difficult, especially when it means potentially reducing funding for something else. NASA's budget is always under pressure, with advocates for different types of missions competing for limited resources. Suggesting that some space exploration funding should shift to ocean exploration would face strong opposition from space advocates, aerospace companies, and NASA itself. Perhaps the better argument is not that we should explore space less, but that we should explore the ocean more. The benefits of ocean exploration, both scientific and practical, justify substantial investment. The ocean affects climate, weather, and ecosystems in ways that impact everyone on Earth. Understanding the ocean better could help us manage fisheries more sustainably, predict dangerous currents and waves, locate resources, track pollution, monitor changes caused by climate change, and discover new species and compounds with potential medical or industrial applications. And there's a certain irony to investing heavily in exploring other worlds while largely neglecting our own. We search for life on Mars while potentially driving ocean species to extinction before we even discover them. We map the surface of Mars in exquisite detail, while leaving vast swaths of our own ocean floor uncharted. We plan missions to Europa and Enceladus to study their subsurface oceans while barely understanding the deep environments in Earth's oceans. The economics and politics of exploration are complex, shaped by history, culture, strategic considerations, and institutional structures that developed over decades. These factors explain why Mars is better explored than the ocean, but they don't make this disparity inevitable or immutable. Priorities can change. Public interest can shift. New discoveries can capture imagination in unpredictable ways. The question is whether we're satisfied with the current balance, or whether we want to make the effort to explore our own planet's final frontier more thoroughly. Before we consider that question, let's look at one more aspect of ocean exploration that connects directly to the search for life elsewhere. The remarkable ecosystems that thrive in Earth's most extreme environments, places that might be analogues for habitable environments on other worlds. The discovery of life thriving at hydrothermal vents fundamentally changed biology. Before 1977, every ecosystem known to science ultimately depended on the sun. Photosynthesis was the foundation of all life on Earth. Then scientists exploring the Galapagos Rift found thriving communities in complete darkness, sustained not by sunlight, but by chemical energy from the planet's interior. This discovery didn't just reveal a new type of ecosystem, it revolutionized our understanding of life's possibilities. Hydrothermal vents form where seawater percolates down through cracks in the seafloor, encounters hot rock heated by magma below, and then rises back up, superheated and laden with dissolved minerals. When this fluid, which can reach temperatures exceeding 400 degrees Celsius, meets the cold ocean water, the dissolved minerals precipitate out, building chimney structures that can reach heights of several stories. These chimneys, called black smokers when the precipitating minerals are dark or white smokers when they're lighter coloured, are the visible signature of hydrothermal activity. The environment immediately around these vents seems utterly hostile to life. The water emerging from the vents is not just hot, it's superheated, under pressure that prevents it from boiling despite temperatures that would instantly vaporize water at the surface. This fluid is rich in hydrogen sulfide, a compound that's toxic to most animals, including humans. It's acidic, it lacks oxygen. And yet, in the interface zone, where this vent fluid mixes with cold, oxygenated seawater, life thrives. The foundation of vent ecosystems is bacteria and archaea, microorganisms that can perform chemosynthesis. These microbes use the chemical energy from hydrogen sulfide, methane, hydrogen gas, or other reduced compounds in the vent fluid to convert carbon dioxide into organic molecules, essentially manufacturing food from chemicals. Different species specialize in different compounds. Some oxidize hydrogen sulfide to sulfate, others oxidize methane. Still others use hydrogen gas or iron compounds. These chemosynthetic microbes are extremophiles, organisms adapted to conditions that would kill most life. Some are thermophils, heat lovers that grow best at temperatures above 80 degrees Celsius. The current temperature record for life is held by a strain called Methanopyrus candleri, which can grow at 122 degrees Celsius or 252 degrees Fahrenheit. That's hot enough to sterilize medical instruments. The microbe not only survives but reproduces at these temperatures, with cellular machinery adapted to function in conditions that would denature the proteins of most organisms. Other vent microbes are barophiles, adapted to high pressure. The pressure at deep-sea vents can exceed 250 atmospheres, more than 3,600 pounds per square inch. Some microbes have evolved waxy cell membranes that help them withstand this pressure. Still others are acidophils or alkaliphiles, adapted to extreme pH conditions, since vent fluids can be very acidic or very alkaline depending on local chemistry. These microbes form thick mats on rocks around vents, create filamentous structures that wave in the current, or exist as free-living cells in the water column. They're the primary producers of the vent ecosystem, converting chemical energy into biomass that other organisms can consume. In this sense, they play the same role that plants and photosynthetic algae play in sunlit ecosystems, but using a completely different energy source. But the really remarkable thing is how larger animals have adapted to exploit this bacterial productivity. Giant tube worms, Riftia pachyptila, can reach lengths of up to 8 feet. They have no mouth, no digestive system, and no way to eat food in the conventional sense. Instead, they have a specialized organ called a trophosome that's packed with chemosynthetic bacteria. The worm's blood contains specialized proteins that bind hydrogen sulfide and oxygen, preventing them from reacting with each other until they're delivered to the trophosome bacteria. The bacteria use the hydrogen sulfide and oxygen to generate energy, which they use to convert carbon dioxide into organic compounds. Some of these compounds are transferred to the worm's tissues, providing the worm with all the nutrition it needs. This is a true symbiosis, a partnership where both organisms benefit and neither can survive without the other. The worm provides the bacteria with a stable environment, a steady supply of hydrogen, sulfide and oxygen, and protection from predators. The bacteria provide the worm with all of its food. The worm grows rapidly, sometimes adding several inches per year, despite never eating anything. Vent clams and mussels have similar arrangements, harbouring chemosynthetic bacteria in their gills. The clams extend their foot down into crevices where hydrogen, sulfide-rich water seeps out, absorbing the sulfide and transporting it to the gill bacteria. The mussels can filter feed like other mussels, but they also rely heavily on their bacterial symbionts, especially when food particles in the water are scarce. Other vent animals are grazers or predators. Vent crabs, sometimes called yeti crabs because of the hairy appearance of their claws, graze on bacterial mats. Some vent snails have chemosynthetic bacteria as well, while others eat the bacteria directly by grazing, on mats or consuming smaller animals. Vent fish, octopuses and sea spiders prey on the smaller animals. The entire food web, from microbes to top predators, operates in complete independence from the sun. These vent communities are temporary in geological terms. Hydrothermal activity at any given vent field might last decades or centuries, but eventually the geological conditions change. Volcanic activity shifts, circulation pathways for the seawater alter, and vents shut down. When this happens, the vent community dies. The organisms dependent on the vents can't simply move to land or shallow water. They're specialized for the deep sea environment. But new vents form elsewhere along the mid-ocean ridge system. So vent species must be able to colonize new sites, sometimes hundreds or thousands of miles away. Most vent animals have planktonic larvae that drift with ocean currents, potentially reaching distant vent fields. This has resulted in a fascinating biogeography, where some vent species are found at multiple sites across ocean basins, while others are endemic to specific regions. The discovery of vent ecosystems led scientists to look for similar environments elsewhere. They found them. Cold seeps, where methane and hydrogen sulfide seep from the seafloor, support communities similar to hot vents but without the high temperatures. These seeps can be associated with oil and gas deposits, with decaying organic matter buried in sediments, or with geological processes that generate methane deep underground. The Gulf of Mexico has numerous cold seeps, each supporting its own community of tube worms, clams, mussels and bacterial mats. Whale falls, the carcasses of dead whales that sink to the deep sea floor, create another type of chemosynthetic ecosystem. The decomposition of whale tissue releases hydrogen sulfide and other reduced compounds, and specialized bacteria colonize the bones. These bacteria support communities that include mussels, snails and other animals similar to those found at vents and seeps. A single whale carcass can support a community for decades as the huge quantity of organic material is slowly consumed. These discoveries reveal that chemosynthesis-based ecosystems are more widespread and diverse than anyone suspected. They exist at varying depths, from shallow waters to the deepest trenches. They can be found in all ocean basins. The microbes involved use a wide variety of chemical energy sources, and the animals that depend on them have evolved remarkable adaptations. The implications for astrobiology, the study of potential life elsewhere in the universe, are profound. For decades, the assumption was that life requires sunlight, or at least energy from a star. This limited the habitable zone around stars to a narrow band where liquid water could exist, and where enough light could reach a planet's surface to drive photosynthesis. But if life can thrive on chemical energy alone, then habitable environments could exist in places we previously dismissed. Europa, Jupiter's fourth largest moon, is covered by a shell of water ice possibly tens of miles thick. Beneath this ice lies an ocean, kept liquid by tidal heating from Jupiter's enormous gravitational pull. There's no sunlight in Europa's ocean, it's far too deep beneath the ice. But Europa might have hydrothermal vents on its seafloor, where water interacts with heated rock, just like on Earth. If it does, these vents could support microbial life, possibly even larger organisms. The discovery of vent ecosystems on Earth made Europa a prime target in the search for extraterrestrial life. Enceladus, a small moon of Saturn, has a subsurface ocean as well. The Cassini spacecraft detected plumes of water vapour and organic compounds erupting from cracks near Enceladus's south pole. Analysis of these plumes revealed the presence of hydrogen, suggesting hydrothermal activity on Enceladus's seafloor. This is exactly the kind of chemical energy source that could support life. A future mission might fly through Enceladus's plumes and collect samples to analyse for biosignatures, all without needing to land or drill through ice. Mars itself might have habitable subsurface environments. While the surface is cold, dry, and bathed in harmful radiation, the subsurface could be warmer, protected, and possibly home to liquid water, trapped in pores in the rock. If microbial life exists on Mars today, it probably lives underground, possibly sustaining itself through chemosynthetic processes using the chemical energy available in Martian rocks and any available water. The study of extremophiles on Earth has provided a catalogue of survival strategies that broaden our concept of habitability. Life can tolerate far higher temperatures than once thought possible. It can survive crushing pressure, extreme acidity or alkalinity, intense radiation, and complete darkness. It can use a wide variety of chemical energy sources. It can form symbiotic partnerships that allow organisms to colonize environments they couldn't inhabit alone. These discoveries inform the design of missions to search for life elsewhere. Knowing that life can exist without sunlight tells us to look in dark environments. Knowing that life can use hydrogen as an energy source tells us to look for hydrogen in planetary atmospheres or in the plumes of icy moons. Knowing that life can form distinctive chemical signatures tells us what biosignatures to search for in rock samples or atmospheric spectra. There's even a hypothesis that life on Earth might have originated at hydrothermal vents. The chemical gradients at vents, with reducing compounds on one side and oxidizing compounds on the other, could have driven the emergence of simple metabolic processes. The mineral surfaces in vent structures could have acted as catalysts, speeding up chemical reactions. The porous rocks in vent environments could have created natural compartments, precursors to cell, membranes. This theory remains controversial and unproven, but it has proponents who argue that vent environments have all the necessary conditions: energy, chemical gradients, organic molecules, and a contained environment. If true, this would mean that the same type of environment that might host life on Europa or Enceladus is the same type of environment where life on Earth began. The exploration of extreme environments on Earth isn't just interesting for astrobiology. These ecosystems contain organisms with remarkable biochemical adaptations that have practical applications. Thermophilic bacteria from hot springs and vents have enzymes that function at high temperatures, and these enzymes are now used in many industrial and laboratory processes. The polymerase chain reaction, PCR, a technique fundamental to modern molecular biology and medicine, uses an enzyme called Taq polymerase, isolated from a bacterium found in Yellowstone hot springs. Other vent organisms produce compounds with potential pharmaceutical applications. The unique pressures of the deep-sea environment have driven the evolution of unusual proteins and cell membrane structures that might inspire new materials. The more we study these extreme environments, the more potential applications we find. But we're only scratching the surface. Each new vent field explored reveals new species, new adaptations, new symbiotic relationships. The 2024 discovery of animals living in cavities beneath the seafloor, in fractured rock below the vents, opened up a new habitat to study. How do these animals survive there? What do they eat? How did they get there? What other subsurface habitats might exist that we haven't discovered yet? The deep sea is Earth's laboratory for studying life in extreme conditions. It's where we can test hypotheses about what life requires, what environments it can tolerate, what innovations evolution can produce when organisms face extreme challenges. Every discovery in the deep sea informs our understanding of life's possibilities, both on Earth and potentially elsewhere. And unlike Mars, where we search for signs of past or present life without yet finding definitive evidence, the deep sea is teeming with life. It's not potential life or possible life or ancient traces of life. It's vibrant, active, diverse life existing right now, accessible to study if we make the investment to explore it. As we develop technologies to explore the oceans of icy moons, the lessons learned from studying Earth's deep-sea ecosystems will guide us. The submersibles designed for full ocean depth could inspire vehicles for Europa's ocean. The sensors used to detect hydrothermal vents on Earth could be adapted to look for similar features elsewhere. The microbiologists studying extremophiles in Earth's ocean could train the astrobiologists who will one day analyze samples from other worlds. In a very real sense, exploring Earth's ocean is training for exploring the oceans of other worlds. The ocean isn't just another planet analogue. It's the best laboratory we have for understanding life in extreme, dark, high-pressure environments. Every deep-sea expedition, every new vent discovered, every new extremophile characterized, is a step toward understanding not just Earth's oceans, but potentially the oceans of Europa, Enceladus, and other worlds we've yet to explore. This brings us to a crucial question. What does the future hold for ocean exploration? What new technologies are being developed? What discoveries might we make? And how does the future of ocean exploration connect to the future of space exploration? The future of ocean exploration is poised at an exciting juncture. New technologies are making exploration more capable and more affordable. International initiatives are accelerating the pace of discovery. And crucially, there's growing recognition that we need to understand our own ocean better if we're going to address global challenges like climate change, resource sustainability, and biodiversity loss. The Seabed 2030 project represents one of the most ambitious goals in oceanography, to create a complete high-resolution map of the entire ocean floor by the year 2030. This international initiative, coordinated by the Nippon Foundation and the General Bathymetric Chart of the Oceans, is bringing together governments, research institutions and private companies to pool mapping data and coordinate survey efforts. As of 2025, about 27% of the seafloor has been mapped at high resolution. That might not sound like much, but it represents enormous progress. In 2017, when Seabed 2030 launched, only about 6% had been mapped. The rate of progress is accelerating as more ships contribute data, as autonomous vehicles conduct long-duration mapping missions, and as international cooperation improves. Reaching 100% by 2030 is ambitious, perhaps overly so. The ocean is vast and mapping requires ship time, which is expensive. But even if the goal isn't fully met, the initiative is driving real progress and raising the priority of ocean mapping in national programs worldwide. Autonomous underwater vehicles are becoming more capable and more numerous. These vehicles can be pre-programmed to follow complex mission profiles, mapping large areas, collecting samples, or surveying specific features. Unlike remotely operated vehicles that require constant human control and are limited by their tethers, AUVs can operate for days or weeks, covering hundreds of miles. New energy systems are extending their endurance. Some AUVs use lithium batteries that can provide power for multiple days of operation. Others use fuel cells or even gliders that extract energy from thermal gradients in the ocean. As battery technology improves, borrowed from the electric vehicle industry and other applications, AUV range and capability will increase. Machine learning and artificial intelligence are starting to play important roles in ocean exploration. An AUV can be programmed to recognize features of interest and adapt its mission accordingly, perhaps investigating a discovered feature more closely, or following a detected chemical plume to its source. Image analysis algorithms can identify species in photographs, count organisms, and classify habitats, reducing the human labor required to extract information from vast data sets. Communication technology is improving as well. While bandwidth for underwater communication remains severely limited compared to terrestrial or space communication, new acoustic modems and optical communication systems are increasing data rates. This allows AUVs to transmit more information during brief surfacing periods, or to ROVs to send higher quality video feeds. New sensor technologies are expanding what we can observe. Chemical sensors can detect minute traces of compounds in seawater, allowing vehicles to follow chemical plumes to their sources. Environmental DNA, eDNA, sampling allows scientists to detect the presence of organisms by analyzing water samples for genetic material that organisms shed into their environment. A single water sample might reveal dozens of species without ever seeing them directly. Advanced sonar systems provide clearer images of the seafloor and can penetrate into sediments to reveal buried structures. Specialized sensors can measure water temperature, salinity, oxygen content, acidity, clarity, and dozens of other parameters, painting a detailed picture of ocean conditions. As sensors become smaller, cheaper, and more capable, equipping vehicles with comprehensive instrument suites becomes more practical. New vehicle designs are being developed for specific tasks. Some are optimized for deep diving, capable of reaching the deepest trenches. Others are designed for long-range operations, able to travel thousands of miles surveying large areas. Still others are small and maneuverable, able to navigate complex terrain like coral reefs or underwater caves. There's growing interest in long-duration missions, vehicles that might operate for months or even years without returning to the surface. Imagine an AUV that's deployed in the Arctic Ocean, spending an entire winter under the ice, mapping the seafloor, monitoring currents, tracking changes, emerging only occasionally to transmit data via satellite. This kind of mission is becoming feasible with improvements in battery technology, navigation systems, and vehicle reliability. Manned submersibles are also seeing advances. The recent upgrades to Alvin have extended its depth capability to over 6,500 meters, allowing it to reach about 99% of the ocean floor. China's Fenduje can reach full ocean depth, over 10,900 meters, carrying 3 people. These vehicles represent the cutting edge of deep-sea technology, but they're also expensive to build and operate. Future manned exploration might involve a combination of occasional manned dives to the most interesting sites with extensive use of robotic vehicles for routine exploration. There's increasing recognition that we need not just to explore the ocean, but to monitor it over time. Climate change is affecting the ocean in ways we're only beginning to understand. Temperatures are rising, acidity is increasing as the ocean absorbs carbon dioxide. Oxygen levels are declining in some regions, sea level is rising. To understand these changes and predict future impacts, we need comprehensive long-term observations. Ocean observing systems, networks of buoys, moorings, underwater sensors, and other instruments are being deployed to monitor ocean conditions continuously. Some of these systems use cables to provide power and communication, allowing them to operate indefinitely and transmit real-time data. Others are autonomous, deployed for months or years before needing to be recovered. Satellite observations complement these in situ measurements. Satellites can measure sea surface temperature, ocean color that indicates phytoplankton abundance, sea level height, wave height, surface salinity, and other parameters. Combining satellite data with in-situ observations provides a more complete picture of ocean conditions. The ocean exploration community is also beginning to leverage crowdsourcing and citizen science. Ships of opportunity, commercial vessels that transit the ocean regularly, can be equipped with sensors that collect data along their routes. This provides coverage in areas that dedicated research vessels rarely visit. Recreational divers, fishermen, and coastal residents can report observations of unusual events or species sightings. While this data needs to be quality controlled, it can provide valuable information. Virtual reality and telepresence are making ocean exploration more accessible. During ROV dives, scientists on shore can watch live video feeds and help direct operations, participating in exploration without being physically present on the research vessel. The Ocean Exploration Trust has pioneered this approach, broadcasting live video from ROV dives and allowing scientists anywhere in the world to participate. Some expeditions even feature watch parties where the public can tune in and experience deep-sea exploration in real time. This accessibility helps build public interest and support. When people can see the strange creatures and dramatic landscapes of the deep sea, when they can watch discoveries happen live, it creates excitement and engagement that can translate into political support for increased funding. The private sector is becoming more involved in ocean exploration. Companies developing underwater mining technologies, for instance, are conducting extensive surveys and mapping of potential mining sites. While their primary motivation is commercial, the data they collect can contribute to scientific knowledge. There's ongoing debate about the environmental impacts of deep-sea mining, but the exploration activities themselves are revealing parts of the ocean floor that were previously unknown. Philanthropic organizations are also increasing their support for ocean exploration. The Schmidt Ocean Institute, funded by Eric and Wendy Schmidt, operates the research vessel Fulcor 2, one of the world's most advanced platforms for ocean exploration. This vessel is available for scientific expeditions at no cost to the scientists, dramatically reducing the barriers to ocean research. The expeditions conducted on Fulcor 2 have resulted in hundreds of new species discoveries and thousands of square kilometers of newly mapped seafloor. Looking further ahead, there's discussion of establishing permanent underwater research stations, essentially underwater laboratories, where scientists could live and work for extended periods. The ocean's buoyancy makes building structures easier in some ways than on land or in space. An underwater habitat wouldn't need to be as massive as a building on land because water provides support. The Aquarius Reef Base, a small underwater laboratory off the coast of Florida, operated from 1993 to 2012 and hosted numerous scientific missions. A new generation of underwater habitats could extend human presence in the ocean, allowing detailed studies of ecosystems and processes that are difficult to observe from brief, submersible dives. The integration of artificial intelligence into ocean exploration will likely accelerate. AI systems could analyze sonar data in real time, identifying features of interest and directing vehicles to investigate. They could process video feeds from submersibles, cataloging species, measuring populations, tracking behavior. They could coordinate fleets of autonomous vehicles, optimizing their paths to efficiently map large areas or to collaboratively investigate phenomena. As computational power increases and algorithms improve, AI systems might even develop hypotheses about ocean processes and design their own experiments to test these hypotheses, operating with a degree of scientific autonomy. This could dramatically accelerate the pace of discovery, though human scientists would remain essential for interpreting results and understanding implications. One of the most exciting prospects for the future is the potential for major discoveries. Every year brings new species, but we might be on the verge of finding entirely new types of ecosystems or environments. The 2024 discovery of animals living in cavities beneath hydrothermal vents suggests there might be extensive subsurface habitats in the ocean crust that we've never investigated. What else is down there that we've missed? Large animals remain undiscovered. Giant squid were cryptids, creatures of legend, until the first photographs of a living specimen were captured in 2004. Colossal squid, even larger, were confirmed to exist but have rarely been seen. What other large creatures might inhabit the deep ocean, avoiding detection because they live in rarely explored regions or because they're too fast or too elusive to capture? Geological discoveries await as well. Each high-resolution mapping survey reveals features that were unknown. Seamounts, canyons, ridges, regions of unusual geology, all might be found as mapping coverage improves. Some of these features could have significant scientific importance, revealing processes we don't yet understand or resources we didn't know existed. The ocean floor contains a record of Earth's history in its sediments and rocks. Analysing these materials tells us about past climates, past ocean conditions, the history of life on Earth. As we explore more of the ocean floor and develop better methods to collect and analyse samples, we'll expand our understanding of Earth's deep history. Perhaps most importantly, future ocean exploration will help us address pressing challenges. Climate change is the defining issue of our time, and the ocean plays a crucial role in Earth's climate system. The ocean absorbs about 30% of the carbon dioxide we release into the atmosphere, and more than 90% of the excess heat trapped by greenhouse gases. Understanding how the ocean is changing, how it will respond to continued warming and acidification, is essential for predicting future climate and developing strategies to adapt. Ocean health is also crucial for food security. Billions of people depend on the ocean for protein, and fishing is a major industry in many countries. But many fisheries are overfished, and climate change is altering ocean ecosystems in ways that affect fish populations. Better understanding of ocean ecology could improve fisheries management, helping us harvest marine resources sustainably. The ocean holds mineral resources, energy resources, and possibly biological resources like new pharmaceuticals. Accessing these resources responsibly requires understanding the ocean well enough to minimize environmental damage. This means knowing what's there, understanding how ecosystems function, being able to predict impacts before mining or drilling begins. The future of ocean exploration is interconnected with the future of space exploration. As we've discussed, studying extremophiles in Earth's ocean informs the search for life on other worlds. Technologies developed for ocean exploration often have applications in space exploration, and vice versa. The isolation, the extreme conditions, the need for autonomous operation, these challenges are common to both frontiers. There's even discussion of using the ocean as a proving ground for space technologies. Testing vehicles, instruments, or operational procedures in the deep ocean can reveal problems and allow refinements before deploying equipment on missions to other worlds. The ocean is more accessible than space for testing and recovery if something goes wrong, making it an ideal laboratory for systems that will eventually explore extraterrestrial oceans. As we look to the future, the question isn't whether we can explore the ocean more thoroughly. The technology exists or is being developed. The question is whether we'll make the investment, whether we'll prioritize ocean exploration, whether we'll commit the resources needed to truly understand this vast realm that covers most of our planet. The ocean remains Earth's final frontier, the last great unknown on our home world, and exploring it is not just scientifically fascinating but practically essential. The exploration of Earth's oceans and Mars are not separate endeavours. They're interconnected in ways that become clearer as both programs advance. The same fundamental questions drive both. What are the conditions necessary for life? How do planetary environments evolve? What can we learn from exploring extreme environments? The technologies, techniques, and knowledge developed for one frontier often benefit the other. Consider the search for life. On Mars, we're looking for biosignatures, chemical or physical evidence that life existed there in the past or still exists today. We're examining rocks, analysing soil, studying atmospheric composition, searching for patterns that biological processes might create. But how do we know what biosignatures to look for? How do we distinguish between biological and non-biological processes? Earth's ocean provides a laboratory for answering these questions. The discovery of hydrothermal vent ecosystems showed us that life can thrive without sunlight, using chemical energy instead. This fundamentally expanded our concept of habitable environments and told us to look for similar conditions on other worlds. The study of extremophiles in the ocean has catalogued the extraordinary range of conditions life can tolerate, from scorching temperatures to crushing pressures to extreme acidity, informing our assessment of potentially habitable environments elsewhere. When we analyse rocks on Mars looking for signs of past microbial life, we draw on knowledge gained from studying ancient stromatolites and microbial mats on Earth, including modern analogues in extreme environments. When we design instruments to detect organic molecules, we test them on samples from Earth's oceans and other extreme environments. When we develop strategies for where to look for life on Mars, we consider lessons learned from finding life in Earth's most extreme habitats. Europa, Jupiter's ice-covered moon, represents perhaps the clearest connection between ocean and space exploration. Europa almost certainly has a liquid water ocean beneath its icy shell, an ocean that might be tens of miles deep and contains more water than all of Earth's oceans combined. This ocean is kept liquid by tidal heating, the same process that creates hydrothermal vents on Earth's ocean floor. Europa might have vents too, environments chemically similar to Earth's vent fields. If we send a mission to explore Europa's ocean, that mission will face challenges remarkably similar to those faced by deep-sea submersibles on Earth. It will need to withstand enormous pressure from miles of water above it. It will need to navigate in complete darkness, using sonar or other sensors, since cameras would be useless in the dark ocean. It will need to be autonomous, since communication delays make real-time control impossible. It will need to detect chemical signatures of potential vent activity and follow those signatures to their sources. It will need to collect samples for analysis. All of these challenges have analogues in deep-sea exploration on Earth. The materials science developed for deep-sea pressure hulls can inform the design of Europa vehicles. The autonomous navigation systems developed for underwater vehicles on Earth can be adapted for Europa. The chemical sensors used to detect hydrothermal vents in our ocean can guide the search for vents in Europa's ocean. The experience gained from decades of deep-sea exploration provides a foundation for exploring Europa. Similarly, Enceladus, a small moon of Saturn with a subsurface ocean, will benefit from lessons learned in Earth's ocean. Enceladus is actively venting water and organic compounds through cracks in its south polar ice, creating plumes that extend thousands of miles into space. A mission to Enceladus could fly through these plumes and collect samples without ever needing to land or drill through ice. Analysing those samples for biosignatures will require understanding what biosignatures to look for, knowledge derived from studying life in Earth's oceans. The technologies developed for ocean exploration have space applications and vice versa. Autonomous systems developed for space missions can be adapted for ocean use. Radiation-hardened electronics designed for space can withstand the corrosive ocean environment. Materials developed to withstand the thermal and pressure extremes of space can often handle ocean conditions as well. Communication technologies see crossover too. While the specific challenges differ, radio waves work in space but not underwater, while acoustic communication works underwater but not in space. The general problems of transmitting data over long distances with limited power and bandwidth are common to both. Solutions developed for one environment often inspire solutions for the other. Power systems represent another area of convergence. Both space and ocean vehicles need compact, reliable, long-lasting power sources. Radioisotope thermoelectric generators, like those used on Mars rovers, could provide power for long-duration ocean missions. Advanced batteries developed for ocean vehicles could find applications in space. Fuel cell technology is relevant to both environments. Navigation and mapping present similar challenges in both frontiers. GPS doesn't work underwater or on other planets. Both environments require alternative navigation methods: dead reckoning using inertial sensors, landmark, recognition using cameras and image processing, acoustic positioning underwater, or star tracking in space. The mapping techniques developed for ocean bathymetry, particularly automated processing of large datasets, are relevant to planetary mapping as well. Sample collection and analysis systems face analogous challenges. Whether collecting rock samples on Mars or collecting biological specimens from a hydrothermal vent, you need manipulators that can work in harsh conditions, sample containment that preserves the sample for later analysis, and analytical instruments that can provide useful data from small samples. Techniques developed for one environment often transfer to the other. There's also psychological and operational overlap. Operating vehicles in extreme environments where direct human access is impossible or very difficult requires similar approaches whether the environment is the deep ocean or the surface of Mars. Mission planners need to think carefully about what data to collect, how to respond to unexpected situations, how to make best use of limited operational time. Scientists need to interpret data collected remotely, making inferences about environments they can't directly experience. The training and skill sets required have significant overlap as well. Planetary geologists often have backgrounds in Earth geology, including marine geology. Astrobiologists study extremophiles from Earth's oceans and other extreme environments. Engineers working on space missions and ocean missions face similar challenges in systems design, material selection, and operational planning. There's substantial cross-pollination of ideas and personnel between the ocean and space exploration communities. Both fields are also grappling with environmental and ethical considerations. How do we explore without causing harm? In the ocean, this means being careful not to damage fragile ecosystems with our vehicles, not disturbing habitats unnecessarily, not introducing contaminants. In space, planetary protection protocols try to prevent Earth life from contaminating other worlds and to avoid bringing potential extraterrestrial organisms back to Earth without proper safeguards. The deep-sea mining debate parallels discussions about space resource utilization. Should we extract minerals from the ocean floor, and if so, how do we minimize ecological damage? Should we mine asteroids or the moon, and what regulations should govern these activities? How do we balance the potential benefits of accessing resources against the risks of environmental harm and the importance of preserving pristine environments for scientific study? Looking forward, the integration of ocean and space exploration may deepen. There's discussion of using the ocean to test systems for space missions. The analog environment of Antarctica's ice-covered lakes has been used to test vehicles that might one day explore Europa. Deep-sea hydrothermal vents could be used to test instruments for detecting biosignatures. Ocean exploration vehicles could serve as testbeds for technologies being developed for other worlds. Educational and outreach efforts are beginning to make these connections explicit. Programs that introduce students to ocean exploration also introduce them to space exploration, showing how the two fields are related. The next generation of scientists and engineers might work on both frontiers, applying knowledge gained in one domain to challenges in the other. The fundamental insight is that Earth's ocean and space are both frontiers, both unknowns, and exploring them requires similar approaches even though the specific environments differ dramatically. The ocean, being closer and more accessible for testing and refinement, can serve as a training ground for space missions. Space exploration, with its higher profile and larger budgets, can develop technologies that eventually benefit ocean exploration. Both fields advance our understanding of planetary processes, the potential for life, and the capabilities of human technology. Perhaps most fundamentally, both ocean and space exploration remind us that there are still frontiers to explore, still mysteries to solve, still discoveries to make. In an age where it's easy to feel like everything is known, like the world has been fully mapped and catalogued, these frontiers offer the excitement of the unknown. Whether we're sending a rover to Mars or a submersible to the Mariana Trench, we're venturing into places no human has been, seeing sights never before seen, learning things never before known. This sense of discovery, this pursuit of knowledge, is fundamentally human. We explore not just because it's practical, though it can be, but because we're curious, because we want to know what's out there, because pushing boundaries and solving challenges is part of who we are. The ocean and space both offer opportunities to exercise this essential human drive. As we conclude this journey through the paradox of exploration, it's worth reflecting on what we've learned and what it means for the future. We've travelled far tonight, from the crushing depths of the Mariana Trench to the rust-coloured plains of Mars, from the discovery of hydrothermal vents to the rovers exploring Jezero Crater, from the challenges of pressure and corrosion to the paradox of knowing a distant world better than our own ocean. Along the way, we've uncovered a story that's simultaneously strange and logical, troubling and hopeful, a story about human choices, technological capabilities, and the frontiers that still await us. The central fact remains striking. We've mapped nearly the entire surface of Mars at moderate to high resolution. We've placed multiple rovers on its surface and operated them for years. We have comprehensive orbital observations from numerous spacecraft. Meanwhile, less than 30% of Earth's ocean floor has been mapped at comparable resolution, and we visually observed less than 1,000% of the deep sea floor. Mars, on average 140 million miles away, is better known to us than the depths of our own oceans. This disparity has multiple causes, as we've explored. The technical challenges of ocean exploration are formidable, in many ways more difficult than space exploration. The pressure, the corrosion, the limited visibility, the communication difficulties, all combine to make deep-sea exploration extraordinarily demanding. Space, paradoxically, is easier to work in despite being harder to reach. Once you're there, once you've survived launch and transit, operating in space is relatively straightforward. Mars has no crushing pressure, no corrosive water, and excellent visibility. Communication is slow but reliable. In terms of area explored per dollar spent, Mars exploration is simply more efficient than ocean exploration. But efficiency alone doesn't explain the funding disparity. Space exploration, particularly human spaceflight and missions to Mars, captures public imagination in ways ocean exploration typically doesn't. Cultural factors, from science fiction to the symbolic importance of space achievement, have created strong public support for space programs. This public interest translates into political support, which translates into funding. The aerospace industry is large and politically influential. NASA has a clear mandate and strong institutional support. Ocean exploration, while scientifically important and practically valuable, lacks the same symbolic power. It's fragmented across multiple agencies with competing priorities. The constituencies supporting it are smaller and less politically organised. The cultural narrative of space as humanity's future, our destiny among the stars, doesn't have a parallel for the ocean. We don't dream of living underwater the way we dream of establishing colonies on Mars. And yet, the ocean remains profoundly important. It covers 70% of Earth's surface. It regulates our climate, provides food for billions of people, hosts the vast majority of Earth's living space and biodiversity. Understanding the ocean is essential for addressing climate change, for managing fisheries sustainably, for discovering new species and potentially new medicines. The ocean is also home to extreme environments that serve as analogues for habitable environments on other worlds, providing crucial insights for astrobiology. The discoveries we've made in the ocean have revolutionized our understanding of life. The existence of hydrothermal vent ecosystems, thriving in complete darkness using chemical energy, fundamentally changed biology and expanded our concept of where life might exist in the universe. The extremophiles found in the deep sea have shown us that life can tolerate conditions far more extreme than we once thought possible. Every deep-sea expedition finds new species, new ecosystems, new phenomena we didn't know existed. But with only a tiny fraction of the ocean explored, how much more remains undiscovered? How many new species, new habitats, new processes? The recent discoveries, hundreds of new species found in just a few months of exploration in one small region, suggest that the unknown vastly outweighs the known when it comes to ocean biodiversity. The future offers reasons for optimism. Technology is improving. Autonomous vehicles are becoming more capable. Mapping efforts like Seabed 2030 are making real progress. International cooperation is increasing. Private philanthropic support is growing. Public engagement through telepresence and social media is building awareness and interest. The rate of ocean exploration is accelerating. But we could do so much more. If ocean exploration received funding comparable to space exploration, if it had the same political priority, the same institutional support, we could transform our understanding of the ocean within a decade. We could map the entire ocean floor at high resolution. We could deploy fleets of autonomous vehicles to continuously monitor ocean conditions. We could conduct comprehensive biodiversity surveys. We could investigate the many unsolved mysteries of ocean geology, chemistry, and biology. This isn't an argument against space exploration. Mars is worth exploring. The search for life elsewhere in the universe is one of the most profound questions we can ask. The technologies developed for space missions have practical applications. The inspiration that space exploration provides has value. We should continue exploring Mars and beyond, but we should also explore our own ocean with the same enthusiasm and investment we bring to exploring other worlds. The paradox of knowing Mars better than our own ocean isn't inevitable. It's the result of choices we've made about priorities and funding. Different choices would produce different results. Perhaps the real insight is that we shouldn't see ocean and space exploration as competing priorities, but as complementary endeavours. Both are frontiers. Both offer discoveries that will expand our knowledge and potentially change our understanding of life and planetary processes. Both require similar technologies and approaches. Both benefit from the insights gained in the other domain. The exploration of Europa and Enceladus, moons with subsurface oceans, will depend on knowledge and technology developed through exploring Earth's ocean. The search for life on Mars draws on insights from studying extremophiles in Earth's most extreme environments, including the deep sea. Space and ocean exploration are part of a unified endeavour to understand our place in the universe, to discover what's possible, to push the boundaries of human knowledge and capability. So as we close tonight, consider the irony. We've sent machines to explore a planet tens of millions of miles away, and we've done it so successfully that we know that distant world better than we know large, portions of our own planet. It's a testament to human ingenuity, to our ability to solve extraordinarily difficult technical challenges. But it's also a reminder that choices about exploration priorities have consequences, that funding decisions determine what we learn and what remains unknown. The deep ocean isn't going anywhere. It will still be there, mysterious and largely unexplored, whether we choose to investigate it or not. The species living in its depths will continue their existence, whether we discover them or let them remain unknown. The geological processes shaping the seafloor will continue, whether we observe them or not. But we will have missed the opportunity to learn, to discover, to understand. The ocean floor is less explored than Mars, but it doesn't have to remain that way. With sufficient will and resources, we could change this situation. We could make ocean exploration a priority. We could invest in the technologies and missions needed to truly understand our ocean. We could discover what mysteries lie hidden in the vast underwater realm that covers most of our planet. The question is whether we'll make that choice, whether we'll decide that exploring our own world is as important as exploring others, whether we'll commit to understanding the ocean with the same determination we've brought to understanding Mars. The answer will shape what we know about our own planet, what species we discover or lose forever, and what lessons we learn that might apply to the exploration of oceans on other worlds. Thank you for joining me on this journey from the deep ocean to distant Mars and back again. If you enjoyed this exploration into one of science's most fascinating paradoxes, please give this video a like and subscribe to the channel for more deep dives into scientific mysteries. And perhaps next time you gaze up at the night sky and spot Mars hanging there among the stars, you'll remember that beneath the waves of Earth's oceans lies a world just as mysterious, just as worthy of exploration, and far closer to home. Until next time, keep looking up, but also remember to look down into the depths we've yet to explore. Sweet dreams, and may your curiosity carry you to new frontiers, whether they lie in space or beneath the sea.